चलो वापस शुरू करते हैं। क्या था भाई, क्या क्या हमने पढ़ लिया था, फटाफट देख लेते एक बार। चलो जल्दी जल्दी, क्या क्या हमारा रिवीजन हो चुका था, क्या क्या सारी बातें हमने कर ली। हम लोगों ने इलेक्ट्रोस्टैट्स के अंदर ये सारी बातें देख ली थी। चार्ज का फॉर्मूला हमने देख लिया। यहाँ पर एक फॉर्मूला का शीट भी मैं प्रिपेयर कर रहा हूँ, जहाँ पर फाइनली आपको जब ये लेक्चर ख़त्म होगा ना, तो उसके बाद आप ध्यान से देखना, उसके बाद ये आपको पूरा लिस्ट मैं प्रोवाइड कर दूंगा। तो ये आपके लिए काम आसान हो जाएगा। जब ये पूरा चैप्टर खत्म होगा तो मैं ग्रुप में आपको स्कैन करके ये पूरा पीडीएफ के फॉर्म में दे दूंगा आपको, जिससे आपके लिए बहुत आसान हो जाएगा ये। ओके चलो, तो ये लिखता चलूंगा। जैसे जैसे हम लोग नए नए फॉर्मूलास को देखते चलेंगे, वैसे वैसे हम लोग ये सारी बातें लिखते चलेंगे। इससे कंसाइज एक जगह पे क्रिस्प हमारा फाइनल मोमेंट रिवीजन होने के लिए एक फॉर्मूला शीट बन के तैयार हो जाएगा। लास्ट क्लास में हम लोगों ने देख लिया था क्यू इज इक्वल्स टू आई टी इंटीग्रल आई डॉट डी, प्रॉपर्टीज ऑफ चार्ज के बारे में बातें हो गई थी। फिर उसके बाद प्रोटॉन और न्यूट्रॉन कैसे बन रहा है, फटाफट देख ले रहे, ठीक है ना, ज़्यादा दिमाग नहीं लगाना। रुको, इसको साइड करने दो, दिक्कत कर रही है। ठीक है, चलो अब यहाँ पर ध्यान दो, समझो। ओके, सो आई होप आपको लास्ट क्लास में यहाँ तक समझ आ गया होगा। कंडक्टर, इंसुलेटर एंड ऑल, ये सारे स्ट्रक्चर्स हमने देख लिए थे बहुत बढ़िया तरीके से। फिर उसके बाद चार्ज डेंसिटी के बारे में हमने बातें कर ली, क्यू लैम्डा एल, क्यू सिग्मा एरिया, क्यू रो इनटू वॉल्यूम। अच्छा, वन मोर थिंग दैट आई हैव एडेड इन दिस नोट्स इज दैट व्हेन यू हैव अ लीनियर चार्ज डेंसिटी ऑप्शन, देन यू कैन एक्चुअली गेट टू थिंग्स इनटू द क्वेश्चन। आइदर यू विल बी गिवन अ वायर और अ सर्कुलर रिंग। सो अगर एक सर्कुलर रिंग दिया रहे, एक वायर दिया रहे, तो आपको समझना होगा कि लीनियर चार्ज डेंसिटी लैम्डा से आपको रिलेट करना है इन दोनों के अंदर। अच्छा, रिंग का सर्कमफेरेंस कितना होता है, ये बात याद रख लेना। रिंग के लिए जो आपका सर्कमफेरेंस होगा वो होगा 2πr, उससे फिर आपको डेंसिटी को रिलेट करना है। तो ये गलती मत करना। बहुत लोग क्या करते हैं, रिंग के सर्कमफेरेंस को के जगह पे एरिया लिख देते हैं πr² और वैसे रिलेट कर देते हैं। तो ये आपको समझना पड़ेगा कि दिस इज अ ब्लंडर, ये नहीं करना है आपको मिस्टेक। आई होप आवाज एंड ऑल आ रहा होगा। एक बार मुझे चेक कर लेने दो, लेक्चर का आवाज तो आ रहा है ना सही से। लेट मी सी इट वंस। साउंड वाउंड सही है, नहीं तो फिर तो आ रहा है ना। हाँ ठीक है ठीक है, आ रहा है। ओके, इंग्लिश में पढ़ाने के लिए आप कह रहे हो, ठीक है, आई विल ट्राई माई बेस्ट। इसमें कोई बहुत बड़ी बात नहीं है, आई कैन डू दैट। बट एक होता है क्या है कि to teach in English requires a kind of means I have to kill my inner emotions, you know, for to teach in English. But okay, then I will try. If you are saying that, no problem with that, we can teach in English. So in the last lecture we have studied all of these. Let's revise them once and for all. So over here in this particular kind of question, all we have to do is take the elemental form q lambda L, which can be converted into an elemental form as a dq equals lambda dx. That's a very easy kind of question. Secondly, here we had a half circular ring with again the same variable lambda and again the same concept of dq is equals to lambda dl. This was a basic example, classical example that we have already done. We have completed the methods of charging, we have done friction, we have completed conduction. One thing keep in mind, whenever two conductors are connected, there will always be a charge transfer. Secondly, their potential will become similar and the charge will transfer according to the dimensions of the radius. So Q is directly proportional to the radius. Secondly, you will also find some more examples. We have done all of this. Okay, so we have completed, nothing more to do. So we have got two particular equations in this topic. One is when the charge distributes, it occurs in the ratio of radius, and when the surface charge density distributes, it occurs inverse to the ratio of radius. So sigma is inversely proportional to radius. That is one thing. Secondly, I have also added one more thing. Sometimes the question says that, let's say we have an initial condition of two spheres which had different radiuses, one is r and 2r, and they have asked to find the final charge ratio. So obviously we will go through this formula, charge directly proportional to radius. Secondly, it was also asked in the question to get the final ratio of the surface charge density, that is sigma. So sigma also becomes inversely proportional to radius. The ratio of charge and the sigma will be different. Q will be directly proportional to radius, but sigma will be inversely proportional to radius. You have to keep this in mind. We have proved this in the previous lecture, so I'm not explaining that anymore. Secondly, one extra thing that can be added in the question is that what will be the ratio of the electric field produced by these two conductors after connecting them. So what we did was, initially they were not connected, now we connected them. So the ratio of the surface charge densities will be inverse to the ratio of the radiuses. Similarly, for charge, we will say that charge is directly proportional to radius, so the ratio of charge will be in the ratio of radius. But One more thing that can be added in this particular type of question is what shall be the ratio of the electric field. So if in the question it is asked that what shall be the ratio of the electric field of the conductors after connecting them, then we will say that the electric field is inversely proportional to the ratio of their radius, similar to sigma. So the pattern in which sigma behaves is the same pattern of the behavior of electric field. So electric field will be again R2 by R1. So henceforth that becomes 2 by 1 because it's inversely proportional to the ratio of the radius, or you can say inversely proportional to radius. That's it. Then we had the particular question of touching and all, identical metal spheres being touched and all. That was all good. Usme koi issue nahi hai. No issues with that. Induction. I hope induction was pretty clear. You had the concept of how we charge a sphere with induction. So keep this in mind that whenever you have to induce an object whenever you have to charge an object by induction, then without earthing, it is impossible to do. So you have to earth the particular conductor to promote charging by induction. I hope this is clear. Secondly, we had this formula of Q induced is equals to minus Q in brackets 1 minus 1 by epsilon r. So this was the induced charge in the target. This was Q with sign. You have to use this formula with sign, and this Q will be of the source that produced the induction, and this is the induced charge on the target. And you have to multiply this with 1 minus 1 by epsilon r. This is a differently proved equation, so we don't have to go for the proving and all. We directly have to remember the result. Secondly, we had the plate kind of questions where I told you about the trick system. So how we have to manage such kind of multi-plate systems. So this is all good. We can do this. No problems with that. Secondly, we had these kind of questions where there was induction as a concept, where there was a charge minus Q or plus Q placed inside a metallic shell. So these kind of questions are very easy to do. We had this concentric metallic shell question where they were shell inside a shell inside a shell. So we had all the concepts of induction applied at once, and we can find the charge of every layer individually. Secondly, induction, this is a very important line. Induction can lead to both attraction as well as repulsion. Keep this in mind. So there is no specification for induction that says that induction only promotes attraction. No, induction can do anything, means attraction as well as repulsion. Secondly, in the complete electrostats chapter, whenever we have these three kind of cases, be sure you have to apply induction. Make sure whenever you get a kind of phenomena where there are two spheres are close enough to each other. So in that case, you can use the concept of induction, or you can see that the concept of induction will be applying in that particular question. Secondly, if there is a point charge close to a sphere, so in this particular case, let's say this is a positive point charge. So in this particular case, the sphere will get induced because of this point charge, but there will be no induction in the point charge. The point charge won't suffer induction. Keep this in mind. The induction will only be seen within the sphere. Okay, that also in the outer sides, because it's a, let's say it's a metallic sphere. So that is why. And secondly, if you have a question of concentric shells where there are two shells, let's say the inner shell has a charge of capital Q and the center has a small particle, charged particle Q. So in this case, you will find induction occurring in both the concentric shells. So whenever you have a case of charged concentric shells, a case when a particle, charged particle, is present close to a conducting sphere, and when two spheres are close to each other, let's say they are charged spheres. So in these scenarios, you can get the indulgement of induction. So make sure whenever you tackle such problems, you have to apply the case of induction, or you can say in that manner, means I'm trying to say that it is not pretty sure that the question will be solved by induction, but yes, the phenomena of induction will be applied in such cases. There can be variation in the question, that depends upon what the question wants or what is it asking, but you have to make sure that in such scenarios, the complete phenomena of induction should not be missed out. You have to keep in mind that induction also will occur in such cases. Now, last class we had the complete conceptual clearization of Coulomb's law. Coulomb's law, let's make this very clear that Coulomb's law is applicable between spheres, is applicable on point charges, as well as it is applicable on static particles. A very good question that I went through. That is, sometimes it is asked that in an atom, where actually is the Coulomb's force or Coulomb's law applicable? So there were two basic options which are confusing. One option was, in an atom, the Coulomb's law is applicable between the nucleus and the electron that's revolving around them. That's the first option. The another option was that the Coulomb's law is applicable between the protons and neutrons within the nucleus. So what shall be the correct answer? The correct answer is that the Coulomb's law is applicable within the nucleus, where the protons and neutrons are binded to each other. So Coulomb's law actually makes the nucleus stable. Okay, defining the stability of an electron has many other aspects to it, not just Coulomb's law. I'm not saying that the force of attraction is not being applied on the electron. It is, but there are other forces as well. So Coulomb's law is mostly, or you can say generally, applicable on static particles. The most important thing is applicable on static particles, along with applicable between spheres as well as applicable on point charges. You have to keep this in mind. Secondly, when two big spheres are getting into Coulomb law interaction, then the distance between them should be finite, not infinite. And that's very obvious for Coulomb's law application. The R should be finite. F is equals to k q1 q2 by r square. The value of k becomes 9 into 10 to the power 9. In CGS, the k becomes 1. K is 1 by 4 pi epsilon naught. We need to make sure that epsilon naught is the value of the relative permittivity of the medium, and this epsilon naught is 8.85 into 10 to the power minus 12. You have to remember this value because when we will be studying the Gauss law, in the Gauss law, sometimes in numerical calculations you will have to put the value of this permittivity of vacuum. Sorry, this epsilon naught is not the permittivity of medium, it's the permittivity of vacuum. Slip of tongue. So epsilon naught is the permittivity of vacuum, and you have to remember this value, 8.85 into 10 to the power minus 12. So keep this in mind. Now this epsilon is the absolute permittivity medium, and epsilon r is the absolute, not absolute, but it is the relative permittivity of the medium. So the formula comes out to be absolute equals permittivity of vacuum times the relative permittivity of medium. So epsilon is equals to epsilon naught into epsilon r. Keep this in mind. This epsilon r is dimensionless, and this epsilon and epsilon naught have the same dimensions. They have dimensions. Keep this in mind. Only the epsilon r, that's the relative permittivity. Whenever we have a term called as relative in physics, most of the cases, any physical quantity has a initiating statement as relative. So that means most of the times that it might have a zero dimension, means it has no unit, no dimension. Okay, so these are most of the cases. Okay, so this can also be called as a dielectric constant of medium, epsilon r, which can also be said as k. Not this k. This k is something else. This is the Coulomb's constant. This is something else. This k is for the dielectric constant k. Okay, so this k is the dielectric constant epsilon r. Dielectric constant of the medium can be given in both ways. Anyway, you have to be prepared for everything. So over here we have some questions. We have done all of these. No worries for that. We have seen this particular type of question as well, where the point charges were replaced by spheres, and now we have to calculate the force between them. This is the important formula. Keep this in mind. Usually it comes in questions. Directly you will get this relation in the answer. If you remember this, you will directly get the answer. You don't have to equate anything. So if the question says that the Coulomb's force is in the air is equal to the Coulomb's force within the medium, then what shall be the distance, relation between the distance in them? So the distance in air equals under root epsilon r times the distance in medium. We have proved this, so we are not going into the proof again, but we will keep the result in mind. So if you keep the result in mind, you will actually be very fast, or you can say you will get the option very fast rather than equating the forces and all. That will take time. Okay, so just keep this in mind, that the distance in air equals under root epsilon r distance in medium. Okay, so I hope this is clear. Vector form, keep this vector form clear as well. This vector form basically includes k q1 q2 by r square. So this is actually, you keep this in mind, that while you're using the vector form, you have to use the sign of the charges as well. Multiple times I've seen students, they actually do not include sign because they have a usual habit of taking the magnitude of charges only. But when you are actually taking the vector form, the sign becomes very important. So the sign is important. q1 q2 has to be taken with sign, and because obviously every vector has to be shown with a direction, so the direction becomes r cap. And when we open up this r cap, so r cap equals to r vector by r magnitude. So when we place or rearrange everything, then we get the final form as, and you have to remember the final form, that's it. So fe, that's in vector form, is equals to k q1 q2 by r cube, that's the magnitude cube, and r vector. Keep this in mind, q1 q2 has to be used with sign because it's a vector form. If you are talking or dealing about normal force of Coulomb, that is the normal F, then you can generally take the magnitude of the charges. But I would rather suggest, most of the cases, the question also asks you to find the direction. So always keep this at the back of your head that you have to use the sign, or you can say that by the direction of arrows even, because obviously giving the arrows on Coulomb's law is very easy. When you see two same charged particles, you will know that they will have repulsive forces, so you know the arrows will be pointing outwards. And when they are two different charges, you obviously know that the arrows will be pointing inwards. So you have to keep at the back of your mind, yes, there can be a chance that the question will, or the option will need to have the arrow or direction within it. So you have to keep in mind directions are important for this particular vector form. So henceforth the final form comes out to be, see, everything at the end comes out at the formulas. If you remember the formulas, you will be good to go. If you know the concept very well but you lack the formula, at the end of the day you are not going to take the marks, you're not going to get the marks. As simple as that. So along with the concepts, you have to be properly memorized with the formulas and the exact formulas, along with at which place you have to use the sign. That's a very important thing. Many people actually miss out the concept that where you have to use the sign and where you don't have to. So in the vector form of Coulomb's law, we have to make sure k, q1, q2 along with sign q1, q2 by magnitude of the distance vector times the r vector in the vector form. This should be proper in the vector form. Now how to explain this r vector? So I have told you already that this r vector should be in the form of, normally in the books it is written final minus initial, initial minus final. So that's a kind of confusing when it is up to questions. You have to remember that target r vector is actually the vector of the target, the vector position of the target minus the vector position of the source. So keep this in mind. Position vector of the target. Target means if the question asks find force on q1, so my q1 is target, q1 is my target, and which particle is applying force on q1, that becomes the source. So position of the source which is applying force on q1 is the r vector. So you can completely make the expression as r vector, position vector of the target minus position vector of the source. Target is the charge particle on which I am calculating the force, and this particle is the source. This position vector is of the source that is applying the particular force. In this particular case, you have the particular terminology is already written because it's a format of question. So in this question, we can see that we are being asked the force on q1 and we have been given the positions of both the charges. So henceforth we can see that this r vector is equals to position of the target minus the position of the source. So I hope this is very clear, and you have to keep this in revision or else you will obviously get out of it. The concepts don't last for long. You have to keep revising them to make them a part of your long-term memory, and that's the only way of proper studying. If you want to crack NEET within 1 year, because obviously the toppers take almost, or you can say an average of 2 years of time. A proper 2 years of studying is necessary if you actually want to get into AIMS or any good MBBS college, good government medical college. I'm not talking about any state level or any just an average medical college. So you have to study for 2 whole year properly, 24 months with full dedication. But if you want to do that within an year, so you have to focus on revision. Only if you can build up the revision part of your preparation, it's more than sufficient, along with questions and variations. Revision without practice is not a revision. So keep this in mind. So superposition principle, we have already dealt with it. What was the superposition principle? So when two particles are close enough, they will apply force or interact irrespective of the presence of a third charge. So whether the third charge is present or not, this third charge won't interfere between the Coulomb's force between two particles. Similarly, the force between these two particles won't be interrupted by this particular third charge. Similarly, the force between this and this charge won't be interrupted by this particular particle. So basically you can say that every two individuals are independent of the presence of a third charge. Similarly for this pair, similarly for this pair, anything you can say. You can take any two at a time. So that's a superposition principle, which is not applicable everywhere. There is a particular scenario where you can apply superposition principle. I hope the questions were also clear. All you have to do is equate the vector form. You have to particularly catch a charge. The most simple probability or the most simple method of doing such kind of questions is you have to particularly hold a charge. You hold a charge and you find that what is the relation of this charge with this one with this one, and obviously you have to draw a vector format, and that's it. It will be enough, more than sufficient for you. And obviously vector summation, we have to do the vector summation for all the charges, and we have already completed. Last class we had the pendulum case all done. We had the scenarios discussed, no problem with that. tan theta, sin theta we had calculated. We had the free body diagram of this particular pendulum case, how the tension and Coulomb's force, electrical force, and the weight was completely resolved, and we had the value of tan theta, that was Fe by mg. Sometimes this alone value can help you a lot. It will save you from multiple calculations. Secondly, we had this discussion on the group that if the masses are variable, then because tan theta is inversely proportional to mass, so if the mass of the pendulum blocks, or you can say balls, changes, so it will be in the inverse ratio of the angle. So m1 by m2 will be equals to tan theta 2 by tan theta 1, and keep this in mind. Keep this very clear. If the masses are different, the angles will be different. If the masses are different, the angles will be different. So keep this very clear. M1, M2, if they are different, theta 1 and theta 2 will be different. That's for sure. But if you have a statement, very important, keep this as well. If the two charged pendulums have equal masses, and are in equilibrium at equal angle, then the charges must be equal. That's a very important line. Two charged pendulums have equal masses. If the masses are equal and the angles are equal, then that is for sure that the charges will also be equal. I hope this is clear. We had all the relations. We had this kind of particular format in which the pendulum was dipped into a liquid. The pendulum dipped into the liquid with an upthrust acting on the pendulums. We had the relation of upthrust being equal to V rho g, as well as the mg was equated to V rho g. This time the mg was written as V rho g in the format that density is equals to mass by volume. So basically replaced mass with density into volume. And because it is the weight of the ball, so the volume as well as density was taken off the ball. Similarly, when we were seeing the upthrust force equals to V rho g, where the volume was taken off the ball but the density was of the liquid. So keep this very particular, or else you will end up doing mistake. Finally, we had the dielectric expression as density of ball by density of ball minus density of liquid. The final dielectric expression was density of ball by density of ball minus density of liquid. Oof. All hectic fellows, man. Okay, now let's start our class. Equilibrium position. Today's lecture starts from now. Let's discuss about equilibrium position. That's a very important topic under the Coulomb's force. After that, we will study the module that we left before. This fellow won't let me teach. Just give me 2 seconds. Just 2 seconds. चाबी बुला दिया या तो उसको पकड़ लेना, एक घूमते रहता है कौन बिना ना, उससे मदद मांगे, ठीक है ना? Okay, where we? Equilibrium position. Let's discuss about equilibrium position. So that's a new topic, fresh and new. So let's give it a go. Equilibrium position. So actually this is talking about arrangement where there are two charges Q and Q2 with a spatial distance of r, and actually you have to find a position where the net force or the net electric field will be 0. Sometimes the equilibrium position can also be said as neutral point. In a question you can be given, or you will have to tackle multiple languages. So sometimes the equilibrium position is also said as a neutral point. Neutral point is a position where the force equates to 0. Either the position of equilibrium can be between these two charges, or it can be outside the scope of these two charges. It means the force of equilibrium, the position of equilibrium can either be between these two charges or it can be outwards. How to find that? We will get to it. So this equilibrium position can also be called as neutral point equilibrium position. So what should be our approach in these particular questions? So the first thing that comes to mind, that you have to see the nature of charges. If both the charges are same, keep sure, because of the same nature, they will have equilibrium position between them. But if the charges are different or opposite, let's say here's a plus and here's a minus, in this particular case the equilibrium position will be outside this particular parameter. That means to say the equilibrium position will be either here or it will be here. Now where to decide whether it is left or it is right? Then you have to see, or you have to move on to the third step, that says that equilibrium position will always be close to the small magnitude charge. So whatsoever charge is the smaller magnitude one, the equilibrium position will be closer to it. Whether the closeness can be within the position or from the outside. Let's take a scenario. We will basically work on examples further. Give me 2 seconds. बोल भाई, बोल व्हाइट कोट मिलेगा मेरे को, हाँ ले जाना। काम मतलब तुम रूम में लगाए क्या? तो आराम से हम रख लेंगे। थैंक यू सो मच। ठीक है भाई, ठीक है। आई एम रियली सॉरी फॉर दैट। आ जाते हैं भाई लोग, देखो अब चलो equilibrium position. So yes, so you have to keep these three particular points in your mind to find the equilibrium position. If both the charges are of the same nature, then the equilibrium position will always be between the charges. If they are of opposite nature, the position of equilibrium or the neutral point will be outside this particular parameter, and the equilibrium position or the neutral point will be closer to that charge which will be the least in magnitude. Okay, let's say Q2 is lesser in magnitude than Q1. I'm talking about the magnitude, I'm not including sign over here. So the charge that will have a less magnitude, let's say Q2, then we can make a guess that the neutral point will either reside somewhere here or somewhere here, depending upon whether these charges have the same nature or opposite nature. Now how to remember this? It is very obvious that such kind of abrupt patterns makes confusion within the exams whenever you are in a MCQ based paper. So this will lead to problems of remember, or you can say that we often get confused with what was the statement, because over here we can find that the things are opposite to each other. So how to resolve this? How to make it a permanent memory? So the best simple scenario over here is you have to take a kind of abrupt guess. The guess is, if the charges are same in nature, being something same. So let's say when you say that two things are similar, so similar things will have a kind of meeting point, or you can say, how to express this in words, I'm not actually being able to get. Let's say in this way, that if two people have a similar nature, so obviously they will end up being together. Okay, but if they have opposite natures, they will end up being away. So that makes a kind of easy for us to memorize that if the charges are similar in nature, the equilibrium position will end up between them. I hope you're getting the point what I'm trying to say. If the charges are similar, then the equilibrium position ends up between them. But if the charges are opposite in nature, then the equilibrium position will be outside them. Okay, so that's a simple kind of way, a more abrupt approach. But yeah, it works. In exams, it will work. And keep this in mind as well, that equilibrium position is always close to the magnitude of charge that is small, or you can say close to the smaller magnitude of charge. Now let's work out on the questions. Okay, let's work out on the questions. Let's see to this. 4Q, capital Q, you have two charges, distance R, find equilibrium position. So let's hide the solution, get a clear approach that what we have to do over here. Over here we can see that both the charges, so actually we can apply these 3 points and we can almost come close to the answer without even using a pen. or a paper. Even by thinking, you can get your answer very close. Even you can eliminate 2 options just by looking at the question and these 3 steps in your mind. Keep this very clear. We can see over here, you just have to listen to the approach and you have to apply the similar pattern with all the questions that you find in future. 2 charges have been given, distances r, find the equilibrium position. So this makes very clear that because the charges are similar, so the equilibrium position will lie somewhere in the center. That's obvious. And one step over. Now the second step is the equilibrium position will lie at which place? It will lie closer to 4q or to q. So we have the answer for that. Equilibrium position always lie close to the small magnitude charge. Henceforth, the equilibrium position will be somewhere over here. That is closer to the smaller magnitude charge, and because the charges are similar in nature, so the equilibrium position is between them. If it were opposite in natures, then the equilibrium position would have been outside but still close to q. The position of equilibrium will always be closer to q, whether it will be inside or whether it will be outside, depending upon the nature of these charges. But one thing's very clear, that the position of equilibrium will always be closer to the smaller magnitude charge. That is either left of q or right of q, depending upon how the charges have a nature, how the nature of charges are. Over here we can see both have the same nature. So no doubt, without any inch of doubt, you can say or you can predict perfectly that the equilibrium position is over here. And even by prediction, this much prediction will help you in eliminating 2 options, and you will have a final to choose. You will have a final left with, you will be finally left with 2 options that you have to choose within. For that, you have to apply calculation. Now, the calculation is very easy. By knowing the exact position, you can actually apply maths in a very easier or in a simpler manner. Or without knowing the position, you will always be guessing whether the equilibrium position will be outwards or inwards and balancing forces and still getting nothing. So there are chances you will get to a wrong answer, okay, by guessing the position differently. Henceforth, if you have a guess of the position, calculation afterwards is a very easy game. Over here, I have done nothing else, just made a guess. I placed a random or assumed a small charge, small q over here. I just assumed it. The question is not given. The question was just asking an equilibrium position. So what I did was I assumed that a small q charge is present at this equilibrium position. And because this charge is present at the equilibrium position, the net force on this charge will be 0. That means this 4q is repelling this small q, and this capital Q is also repelling this small q in equal magnitudes in opposite directions. So this small q is facing this particular force from capital Q and this particular force from 4q. Henceforth, both of these forces are equal, and I equated both of these, cutting and obviously because we are equating these 2 equations, so capital Q goes off, small q goes off, k comes out, and we have a simple equation 1 by x square equals 4 by r minus x square, making r equals to 3x. So we have the final answer, x equals r by 3. So this makes your answer very easy. Just by guessing the equilibrium position, you can get to the answer in a faster way. Rather than guessing whether the equilibrium position was inside or outside, it would make a mess out of it. Now let's see some other examples. So again, you don't have to see the solution, just try to make an approach within yourself. Let's see, over here we have minus 4q, we have q, the distance is r. The first thing that comes to mind, because the charges are opposite in nature, we can be pretty sure that the equilibrium position is not lying between them. So it would either be lying left to minus 4q or right to q. Now the third point indicates us that the equilibrium position will be closer to a lesser magnitude charge. Henceforth, the equilibrium position will lie somewhere close to capital Q. So this makes our calculation much easier, and now we can make a proper guess. Now we have to find the equilibrium position. We will do the same thing. We will place a random, or we will assume a small charge, small q over here, and we will find the force due to capital Q and the force due to minus 4q at this position, and we will equate both the forces. We will get the equilibrium position. So that becomes very easy. Similarly, what I did was, the distance was assumed as x from capital Q, because obviously, as I said, the equilibrium position will always be present close to the smaller magnitude charge. Henceforth, over here, I equated the forces applicable due to capital Q, this force, and minus 4q led to the application of this particular force, and the directions are opposite. So we can clearly see that the forces are equal and opposite. Henceforth, equating both of them to get the neutral position, we get R equals X. So that's very easy. You have the answer with you. We have another question, but this time the pattern is a bit different. Over here, what you have to do, you see, keep this in mind. This is a new variety of question. Not this one I'm talking about. Let's skip this one. 4q equilibrium position. Obviously, because the charges are equal in magnitude, obviously you don't have to do anything. Just say that because they are same nature charges, obviously the equilibrium position will lie between them, and between as well as in the midpoint, because the charges are equal. So that is very obvious that the equilibrium position will be exactly the midpoint between the charges. So that's a very easy question. Let's move on to the next question. This is very important. So when you have a charge distribution of -4q and +4q kept at a particular distance, let's say r, and now we have been asked to find the equilibrium position. Now, because these two charges are opposite nature charges, so obviously the equilibrium position will not lie between them. It will lie somewhere outwards. Now there's a problem. The problem is, because both the charges have equal magnitude, then where to place the equilibrium position? So you can place it anywhere, because both of them have equal magnitude. So it won't make any difference. You can place the equilibrium position right to +4q, or you can do the same thing with -4q. You can either place the equilibrium position left to -4q. It will give the same answer, no difference with that. And again, similar, we have to equate the forces at these two particular points. Similarly, this particular -4q will cause attraction, as well as this particular 4q plus 4q will cause repulsion, because I have assumed a positive charge. And this attraction and repulsion will be equated. That is very easy. You don't have to consider sign over here, because you are already equating both of them. Okay, so you don't have to consider any kind of sign, because over here we are only dealing about magnitude. No one is asking to find the direction of force or vector form of force. So there is no particular requirement to deal with the sign. You can only equate the magnitude, and henceforth you will get. Now, the most important thing you get over here, when you equate both of these, you will find that r equals 0. That means in such a case of representation, in a case of -4q and +4q, there is no equilibrium position, because when you do such kind of question, you will get to know. And now, because you know, whenever a question comes something like this, you keep this very clear that if two opposite charges which are of equal magnitude, they will never have an equilibrium position, because they will always attract and they will collide in the center, or you can say they will finally mutually interact and they will collide in the center. They will never have an equilibrium position, because they are equal in magnitude and exactly opposite in nature. Henceforth, they can never have any equilibrium position between them. And by calculation, we showed also, because I'm not telling any kind of myth, I am proving it with calculation. So I have proved that the r comes out to be 0, and 0 means the equilibrium exists as infinity. There is actually no equilibrium case in such kind of charge arrangements when there is -4q and +4q. Now let's change the variation. We have been asked to find the force on this particular q when the q. So this is a kind of, this particular variation will only show you how to place the direction of force. Okay, this is not about equilibrium. This is only about the direction of force, how force acts. We have +4q, -4q arrangement at a particular distance, and we have a small q placed midway. So when you have placed this small q midway, you will find that this -4q will attract this particular q, and +4q will repel the small q. Henceforth, the net force is totally in the rightward direction. Therefore, this small q will never be in equilibrium. It will be pushed rightwards. Let's shift this q to the equatorial position, upwards. Over here, we will see that this +4q will repel this q in the opposite direction. This -4q will attract it towards itself. Hence, the net force will be again in the I head direction, positive x-axis. So this q is also not in equilibrium. And the similar way, if in the similar way, if you shift this q downwards equatorially, then you will again see the same scenario happening. That is, this q will get a net force rightwards in the positive I direction. Henceforth, such kind of arrangement, a arrangement where there are charges of opposite nature and equal magnitude, you will never find a equilibrium position. You will never find an equilibrium position. Whatever charge you place between them, it will always get a positive net force. The net force will never be zero, and because the net force can never be zero, there can be never an equilibrium position or a neutral point, because our explanation says at an equilibrium position, the net force and the net electric field should be zero. Okay, not just force, electric field also is zero at an equilibrium position or at a neutral point. Let's deal with some statements. All charge arrangement systems don't have equilibrium positions. Exactly, this can be an exact statement in the exam. Okay, an exact statement in the exam can be asked that do all charge arrangement systems have an equilibrium position? The answer is no. It is not necessary that every charge arrangement will surely have an equilibrium position. That's not necessary. Secondly, if you have a question, a pattern of question where you are given a regular polygon, let's say a triangle, a rectangle, or a hexagon, or anything, let's say a pentagon, or you can increase it to n times, a regular polygon which has equal sides, and you have same charges at all corners, keep this in mind. The center will be the equilibrium position. So you don't have to calculate. For such questions, many students start vector calculating, showing the signs and starting with the vectors and all. You don't have to do anything. Just keep such kind of variation. If there is a regular polygon with all sides equal, hexagon, rectangle, square, whatsoever, not a rectangle, I would say a square would be a better fit, because a square has all the sides similar. Saying a rectangle will not have the equilibrium point at the center, okay, because a rectangle don't have equal sides. What I'm talking about is a regular polygon should have all the sides similar. So a square is a better fit, a equilateral triangle is a better fit, and a regular hexagon is a better fit. And mostly questions revolve around this kind of variations. So any regular polygon with same charges at all corners. So either all the charges are positive or all the charges are negative, but it should be same. The nature should be same. The equilibrium position will surely be at the center. Many times while solving such kind of questions, what students get confused with is the distance of the vertex from the center. So please keep this in mind. For equilateral triangle, the distance of vertex from the center is a by root 3 times. A is the side. Similarly, for a square, the distance of the corner from the center, distance between the corner and the center, is a by root 2 times. As you can say that the complete diagonal of a square is root 2a times. So you are actually looking at half of a diagonal, a by root 2. Similarly, when you are talking about a equilateral triangle, so the line that stretches from the vertex to the middle of the another line, this complete line is a median, and the length of a median in an equilateral triangle is root 3a by 2. Root 3a by 2. Yes, I'm pretty sure it is right. Root 3a by 2, and the distance from the vertex to the center is a by root 3. Actually, the ratio of this length and this length is 2:1. This complete median length is root 3a by 2, and these ratio, the ratio of the line from the vertex to the center and then from the center to the midpoint of the another line, this lies at a ratio of 2:1. So if you divide root 3a by 2 in a 2:1 ratio, you will get this. It is not simple maths. You have to actually calculate the ratio. You are not doing divide by 2. It is not divide by 2, just like in the case of a square. In a square, what we had to do, diagonal length by 2 was this length, a by root 2. But over here, you are not doing divide by 2. That will only give you a wrong answer. So remember this. Don't get into further calculation. Just remember that for an equilateral triangle, the distance from the vertex to the center of the triangle, that's also called as the centroid. So centroid and the vertex have a distance of a by root 3. And similarly, for a hexagon, the distance from one corner and the center is simply the side A. So that's very easy to remember. We have another question like this. -3 Coulomb charge is placed at the center of a square. So we don't have to calculate, because we just saw that this square has a equal charge distribution, -q at all the corners. So obviously the center will be an equilibrium position, and because the center is an equilibrium position, this -3 Coulomb charge is not getting any force, is not feeling any electric field. Henceforth, the F net is 0 because it is an equilibrium position. Now the question was asking what is the net force on the -3 Coulomb that was placed in the center. So our answer will be 0, because the net force on this particular 3 Coulomb, -3 Coulomb, is nothing. It's 0 because it's an equilibrium position. Now, when we talk about equilibrium, we have to keep two things in mind. One is the equilibrium of the particle and another is the equilibrium of the complete system. The questions can be asked in such a way to check your knowledge, whether you know the complete knowledge of equilibrium or not. Equilibrium can be of the particle or can be of the system. Particle, when you're talking about the equilibrium of the particle, you only have to see whether the particle is at equilibrium. Let's say you have multiple particles which are arranged in a random way. Just take an example how to take I don't have any particular object with me now, but you can just assume, let's say you have a particle in the midway of a system. Okay, we have a system of charges surrounding this particle. So when we say that this particle is at equilibrium, that means the net force on this particle should be equal. Net force, the particle should be in equilibrium. When I am saying this particle is at equilibrium, for me, the equilibrium of the system does not matter. Anything that matters is the equilibrium of just this particle. But when I say the complete system is at equilibrium, that means this particle should be placed at such a position that not only this particle gets equilibrium position, but the complete system is also stable. So that is how we define the system's equilibrium and the particle's equilibrium separately. Particle being at equilibrium, we only focus upon the particle. System being at equilibrium means the complete system is at equilibrium including the particle. Now examples will give a better understanding of this particular concept. Okay, let's move on to examples, because obviously the only place where we can learn is by solving examples, seeing questions, seeing variations. We have arrangement plus q, similar charges, distance is r. Find position and value of charge q for its equilibrium. And the next question asked is for system's equilibrium. So first case is asked, you have to place a small q at such a position where this q is at equilibrium. That's it, nothing else. But you have to place this small q at a place where the complete system is at equilibrium. So let's discover the cases. The first scenario comes out to be, you have to understand both of these diagrams. This is very crucial for better understanding. What I have done is, obviously I know that because these charges are similar in nature, and we have already been told that when the charges are similar in nature, the equilibrium position lies between them. We have already been told that when the charges are similar in nature, the equilibrium position lies between them, right? But when you place a charge between them, this charge will surely be in equilibrium. That is no doubt for that. But you will find that in between these plus q charges, if you place a plus q, small q, plus a small q, you will see that this plus q is at equilibrium, no doubt, because it is at an equilibrium position. But you can see that this capital Q and this capital Q are not at equilibrium, because this plus q repels this capital Q, as well as this capital Q also repels this capital Q. Henceforth, this capital Q is getting a net force in the leftward direction, or you can say minus I direction. And in the same way, this plus q is also getting a net force in the plus I direction. But this middle particle is at equilibrium, no doubt for that. Because in this particular question, we were only thriving for the equilibrium of a particle. But we want to find the complete system at equilibrium. So for the complete system at equilibrium, all the particles must have net force 0, or all the particles should have a neutral point. In this scenario, what we can do is, we can change the nature of this intervening charge. If we change the nature of this small q from plus q to minus q, now when you do the vector summation of all the forces, you will find that before and after as well, this q was always in equilibrium. Because as we have already discussed, the position of equilibrium has nothing to do with the charge we are placing over there. Whether be it minus q, whether be it plus q, it will always be at equilibrium, because this equilibrium position between the charges is fixed. So particle is at equilibrium in both the cases, whether be it the case of plus q, whether be it the case of minus q. But for the complete system to be at rest, you have to make the system, or you have to arrange the charges in such a way, or rather it would be better to say that you have to choose a charge in such a way that its nature supports the equilibrium of all the side by charges. Over here, when we did the vector summation of the forces, we found that these terminal charges were getting net forces outwards. But when we shifted the plus q with minus q, this minus q was also in equilibrium, no doubt for that. But because of the attractive force, this plus q and minus q suffered, and the attraction between minus q and plus q that these two suffered made these terminal charges at equilibrium. Because over here also we can see that the net forces became equal and opposite in directions. Henceforth, this is a situation required for the complete system to be at equilibrium, and this is a complete scenario where the particle is at equilibrium but the system is not at equilibrium. So this particular scenario sets a field where the system is not at equilibrium but the particle is at equilibrium in both the cases. Particle's nature has nothing to do with its equilibrium. Whether the particle is plus q or minus q, it will always be at equilibrium, but the system's equilibrium has to do with the nature. So in this scenario, we were seeing that the system was not at equilibrium, but over here, we found that the complete system was at equilibrium. That's very important. So the third charge q must be opposite in nature, that is minus q. That we found by vector summation. But every time in a question, we won't be doing this. Every time when you are asked a question, you won't be calculating all the vector directions, and you won't be seeing that whether the systems are also getting the net force 0, or rather they are getting some force. So this is a kind of hectic procedure. What we will be doing, we will set up a scenario. If you are given a arrangement of plus q1, let's say this is q1 and let this be q, okay, or you can take it as q2, no matter with that, and you are placing a small charged particle minus q at the center, and this distance of minus q with q1 is x, and the complete distance between q1 and q2 is r. So two distances, keep this very clear, one is x and one is r. Okay, so this x is the distance between minus q, that was the new particle introduced in between q1 and q2, and this x is the distance between minus q and q1. Why I am mentioning this as q1? Because when you will apply the formula, you must be very careful with applying these charges at the correct position, because if you make a slight mistake in placing the charges, if you misplace q1 with q2 in the formula, the complete answer comes opposite, and the examiner will be prepared with a different option in the different answer in the options. So your answer will come and it will match with the options, and you will be very confident that my answer is correct. But obviously when you get to home and you match the answer key, you will find that there has been something fishy. So what's the formula? How to work this out? You have to keep this formula in mind. This creates your calculation better, and secondly, it will make your calculation faster. You don't have to equate the forces every time. You don't have to make a vector summation and all. Just keep this in mind. If you have arrangement of two charges q1, q2, and you have to place a small charge q in between them, whether be it plus q or minus q, that is a different matter, because we have seen that whether be this plus q or minus q, the particle is always at equilibrium. But for the system's equilibrium, we need this charge to be opposite in nature. So how to get a one word answer, direct answer, without doing any kind of vector summation? Just by one word answer, I mean to say that you read the question, you had the answer. You need not draw any kind of arrangement. You need not draw any kind of force, parallel, not parallel, anti-parallel. You need not draw any kind of system arrangements. All you have to do, you have to read the question, you directly have to apply the formula. How to get an approach for that? You have to keep in mind that whatever the two charges are given in the question, you have to assume a charge as q1, and you have to fix that charge as q1. You won't shift your q1 charge. Let's say the value given was 9e and e. So for my mind, I made 9e as q1, 9e, let's say the charge of 9 electrons. Okay, so I made that 9e as q1. And now when I use the formula, I will make sure that wherever q1 comes, I will use 9e only. And whenever q2 comes in the formula, I will use the other charge. Secondly, this x is the distance of the equilibrium point from q1. Always make this sure. So whatever your q1 is, this x will be a distance from q1. Many times students do grab the formula, but during the exam, they actually forget where to apply it, how to apply it. Okay, so many times that is the case. So I hope this is very clear to you. The sounds proper? Yes, okay, there's no problem with that. So the formula says x equals under root q1 by under root q1 plus under root q2 times r. R is the distance between both the charges. Secondly, this q, that what shall be the nature and the magnitude of this q, will come with one formula. You don't have to put anything extra. all you have to do is calculate for small q, and this small q will be equals to minus q1 q2. This has already been worked out, so these are already proved. You only have to remember the formulas. So this small q that will be placed in between, you don't have to focus about the charge will already be calculated by the sign of the formula. If you just apply the formula, you will get the q with sign, so you don't have to apply anything extra over here. If there was anything fishy over here, I would have mentioned it, but you don't have to worry for anything. The only thing you have to keep in mind is the distance x is from q1 charge, and once you fix your q1, make sure you always use that charge at the position of q1 in the formula. Don't intermix q1 and q2. Just you have to fix two things in mind. You have to fix a charge as q1 and the distance from q1 as x. Obviously the total distance is r, and the midway, or you can say the between distance, is x. So x equals under root q1 by under root q1 plus q2 times r, that is the distance between both the charges, and the nature and magnitude of q will come with this formula, that this small q that was placed in between them was minus q1 q2 by under root q1 plus under root q2 whole square. I know this kind of formula looks a bit big and kind of problematic to remember, but trust me, if you remember this formula, it will take hardly 2 times revision. 2 to 3 times it will take you to revise. Once you have a grab on this formula, your questions will have a amazing speed. You will feel that the speed has increased. So you don't have to equate continuously for a long time, or and there are still chances that your answer would be wrong. So this formula will give you the accurate answer. Just make sure you are correctly seeing the x and the q1, or else you will again end up doing a mistake. So let me write these formulas in the formula sheet that you are preparing, so that at the end of the chapter we will get a final formula chart. All the formulas have already been written pre-hand. For equilibrium position, we have a new formula over here. Okay, make sure, one thing that I had to mention over here, you make sure that these q1 and q2 should be used with sign. Only then you will get the correct sign of small q. In the formula, this q1 and q2 should be used with sign, or else secondly the examiner will give you charges which will be possible to square root of them. Means you can say perfect squares. You will get perfect squares. The charges will be perfect squares, so that you can work out upon the under root function. So don't worry for that. This under root won't be problematic for you. The charges will be given such that it will be a perfect square, so you can under root them easily. So this is q1 q2. The distance between them is r. I make this very clear that whatever my equilibrium position be, the distance is x from q1, and this is the charge q that I have to place over here. So the formula comes out to be, that is our basically in the formula sheet we're writing this. We have already studied this in the note. X equals under root q1 by under root q1 plus under root q2 times r, and this q will be evaluated by the expression minus q1 q2 under root q1 plus under root q2 whole square. That's it. And you have to use q1 and q2 with sign, so that you get the correct sign of small q. These charges must be used with correct sign. So let's say the question says this is plus q1, this is minus q2. So in that case, because you will use plus q1 and minus q2, so this minus will get converted into plus, and the q will get a positive sign. So you have to make sure that this q1, capital Q1 and capital Q2 have to be used with sign. So let's keep our formula chart aside and focus on this question. Now, what was the question? The question said you have two charges plus q, a distance r between them. Now we have to find a position where this small q will be at equilibrium and the system will be at equilibrium. So the same thing can be obtained over here like this. You can get the position x by the formula under root q1, which was simply q in this question, by under root q1 plus under root q2 will be 2 under root q, because they are same values. Okay, so that 2 times becomes 2 times into r. So the final answer comes out to be r by root 2. Similarly over here, q, the value of q can be evaluated as minus q1 q2, q1 and q2 both being q. So therefore it comes minus q square by q1 plus q2 whole square. So q1 plus q2 was 2 root q. 2 root q whole square becomes 4q, minus q square by 4q becomes minus q by 4. So the charge that was introduced between them should be minus q by 4. And henceforth your answer is at one instant. You don't have to equate any force. Only you have to remember the formula and you have to correctly apply x with q1 and you will get a proper answer, correct answer, accurate answer. Just keep things in mind that you have to use the sign properly, as well as you have to use the distance x and q1 properly. This is very crucial for the answer. Let's see two statements which are very important. For third charge equilibrium, value could be anything for plus minus q. So the answer, let's listen to this again. For third charge equilibrium, that is the equilibrium of this particular charge. This is the third charge that was introduced between two of them. So for the third charge's equilibrium, the value could be anything. It can either be a plus q, it can either be a minus q. But for the complete system's equilibrium, the value of that third charge is specific. If you want the complete system to be in equilibrium, you have to choose a specific charge nature small q. You cannot take any small q because plus q won't give the system at equilibrium, but minus q will give the system at equilibrium or will keep the system at equilibrium. Henceforth, if you want just the equilibrium of the third charge, then any value of q will work. It can either be plus q, it will either be minus q. But if you want the complete system to be in equilibrium, then you have to use this particular formula that will give the complete system's equilibrium. So the question will ask that what kind of charge should we introduce so that the complete systems is at equilibrium. So use this formula, you will get the value of q in an instant. You don't have to work out on any force management. You don't have to do anything. You don't have to equate the forces. You don't have to take vectors and all, nothing. Just a formula and that's it. You will get the answer. But what happens if the system is big? What happens if the system is not like this? This particular formula is only applicable when there is a linear arrangement of particle. You have a linear arrangement and you are introducing a third particle between that. So such kind of arrangement will have these formulas. Don't apply these formulas everywhere. And these kind of questions often come. So these formulas will be handy for you. Don't think that these questions are not going to come. So what's the use of learning these formulas? These questions are oftenly asked and henceforth these formulas will come handy to you. And it will be very helpful while the exam time to save your time. During the exams, that will save your time. Let's see this question. You have an arrangement of charge capital Q at the corners of a square. The distance is x. Find position and value of Q for system's equilibrium. Now, keep this in mind. Find position and value of Q, small q, that should be introduced in between this for system's equilibrium. One thing that we are very clear with, because this is a regular polygon and because all the charges are similar, the equilibrium position is for sure to be at the center. But what should be the sign of this small q so that every charge is at equilibrium? Because we said for this particle's equilibrium, any sign is valid. You can either take this small q as plus q or minus q for this particle's equilibrium. But if you want the complete system to be at equilibrium, there must be a specific sign of this small q so that the complete system is at equilibrium. Let's do a thing. We won't be doing anything extra, just we will take a random guess. We will keep the small q particle at the center and we will try to find out the forces that it exerts on a side particle capital Q. What our aim is? Our aim is to find whether the system is at equilibrium or not after placing this small q. We are very sure that this small q will always be at equilibrium because the position of this small q is at the center and the center is the position of equilibrium. Equilibrium position is the center. In such kind of arrangement, the equilibrium position is the center. That is for sure. Okay, that's not going to change. But whether the system is at equilibrium or not, for that we have to counter the forces. So let's counter them one by one. You will find that this capital Q is getting a repulsive force from this capital Q. So hence the arrow in this direction. Similarly, this capital Q is getting a repulsive force from this capital Q and hence an arrow in opposite direction. Similarly, the diagonally opposite capital Q also repels this capital Q. So we can see that this capital Q should be moving away from the corner. But because we want this corner particle or this capital Q to be at equilibrium, there must be another force that must be equating these three forces. so that this capital Q remains at equilibrium. And this attractive force should come from this central particle small q. Now what we are going to do is, we are going to equate these three forces with this particular force. We are creating this scenario in our mind because the question asks that we need the system to be at equilibrium. For the system to be at equilibrium, you have to make sure that every particle of this particular square is at rest or at equilibrium. So we have to equate all the forces, the one force that counters all these three forces. Now these three forces have to be vector componented, and for that we already know that the diagonal's half length is x by root 2. What we are going to do is, it's a very easy task. This particular force, keep this in mind, this particular force is directly coming from the diagonally opposite q, and this length is root 2q. Okay, this complete length of diagonal is root 2q. No problem with that. So what we are going to do, we are going to write all the forces. So first force that I wrote over here, that is the force between these two opposite diagonals, that is kq square by root 2x whole square, that becomes 2x square. Now you have the force, this one and this one, to be combined in this particular direction. And because it is a right angled square, so this angle will be 45 degree. So compounding these two forces along this diagonally, you can say parallel to this diagonal, combining these two forces parallel to this diagonal will require to component it as 2f cos theta. Listen this very carefully. This force is F, okay? But these two forces have to be compounded along with F, and that will become 2F cos theta. Because this force will be compounded as F cos theta, and this force will be compounded as F cos theta, componented as whatever you say. Henceforth, the final equation, your final expression comes out to be F plus this root 2F. And the f being the same because the distance is x and x, henceforth this f is kq square by x square, root 2 times. Why root 2 times? Because cos 45 is 1 by root 2, and 1 by root 2 times 2, that becomes root 2. So root 2 times f plus this f that was coming from the diagonally opposite charge equals the force of attraction between this corner q and the central small q. So this force of attraction will equate these three forces. Henceforth you get the expression at the RHS, that is k capital Q small q divided by the half of the diagonal length, x by root 2 whole square, so that becomes x square by 2. And when you equate all of this, you will find the value of small q, and the value of small q comes out to be minus capital Q 2 root 2 plus 1 by 4. And that small q, obviously the answer will be minus. You don't have to add anything extra. You don't have to add this minus. This minus will already be present in the answer. So you keep this in mind, that when you equate these, all of these forces, one thing I have already mentioned, that this arrow is in the direction of small q. What if I would have said that this small arrow is also in the direction of this f? In that case, I would have got the answer minus, again the same thing, because if you change the direction as well, the answer won't change. So I am telling you, the only thing you have to do is equate the forces already, and you will get the small q that should be placed in center should be minus capital Q in bracket 2 root 2 plus 1 divided by 4. That small q should be an opposite nature one to make the complete system at equilibrium. So let's read this line. अगर पूछा होता चार्ज का इक्विलिब्रियम चाहिए तो कोई भी value of q will be at equilibrium at center. What does this line mean? So if in the question it would have been asked that what shall be the value of small q for the equilibrium of this particular small q. So it can be anything. It could have been plus q, it could have been minus q, because only for the equilibrium of this particle the sign does not matter, because this particle will be at equilibrium at all cost, whether be it at plus q level or whether be it minus q. But for the system's equilibrium, you have to be specific with the sign. And if you want the complete system to be in equilibrium, this small q that is placed in the center should be oppositely charged. So what are the types of equilibrium? We are dealing basically with two types of equilibrium. One is a stable equilibrium position, that's minimum potential energy position. Whenever any particle is at a stable equilibrium position, the potential energy is least. Whenever the equilibrium is unstable, then the potential energy is maximum. Such kind of arrangement we are going to see in work, power and energy. I'm just taking a hint of it and trying to explain it to you. And if a particle is just like lying on a ground, so this kind of a position is called as a neutral equilibrium position. Now these are just types of equilibriums, has nothing to do with this particular topic. Now this will actually be helpful in dipole when we will be studying electric dipole. In that particular case, you will get to find that when the potential energy is least, so that automatically becomes the most stable equilibrium position. So you will be asked in the question that find the most stable equilibrium position of the dipole. So such kind of questions comes. Secondly, it will be asked that what is the most unstable position of the dipole. So the position where potential energy is maximum, that is itself the position of unstable equilibrium. I hope this is very clear to you. Let's move on to our next question. This next question is very important, very crucial. Please see this particularly. You have an arrangement capital Q and a small q. Find equilibrium if a small q is displaced axially and equatorially. First imagine, before saying anything, what is the ask of the question? What is the demand of the question? If you want that find equilibrium if q is displaced axially, we can already see that the charges are similar in nature. That means the equilibrium will be somewhere between them. And because both have an equal magnitude, so we can be pretty sure that the equilibrium position will be somewhere in the midway. Now we have been asked to displace this small q axially. Let's find out the forces acting on this small q. The forces acting on the small q is repulsive force from this q rightwards and repulsive force from this capital Q leftwards. That means this small q can be said to have a kind of equilibrium position because both the charges are pushing them in rightward and leftward equally, because this small q will be in the center. But what happens if we shift this small q axially? So the moment you shift this small q axially, you will find that the distance between small q and capital Q will be reduced, and once the r reduces, the force increases, because Coulomb's law says the inverse square law. Coulomb's law follows the inverse square law, that is, force is inversely proportional to r square. So as r decreases, force increases. That means when this small q comes close to capital Q, the leftward force will increase, because this capital Q will try to push it more harder, because the r was decreasing. So this capital Q will try to push it more harder towards the left. And because this small q was moving away from this capital Q, so the force of repulsion between this capital Q and small q will start decreasing. Henceforth, as we push this small q axially, we will see an oscillation motion. Or you can say an SHM, depending upon how much the displacement is. If there is a very little displacement, then we can say that the motion shown by this small q will be simple harmonic motion. But if it is a large displacement, then that becomes an oscillation. Okay, so keep this very clear, very important. This is a very important concept. So sometimes what the question does is, it just asks you that the charge is displaced. In that case, by default, you have to assume an axial displacement. Sometimes the question will not mention whether the displacement is done in an axial position or an equatorial direction. In that case scenario, by default, you have to consider an axial direction for sure. So axially, by default, if direction of displacement is not mentioned, then you have to consider axial displacement by default. And as we said, because this small q was shifted axially, so this capital Q will try to repel it more towards leftwards and try to keep it again at the equilibrium position. Henceforth, such kind of a displacement becomes a stable equilibrium. Stable equilibrium means whenever you displace a particle, it will again return to its initial path. Just as we saw in this case, when the ball was present in such kind of a ball-like structure, it was in stable equilibrium, because a slight shift to this ball will cause the ball to slide downwards again. So this is a stable equilibrium position. But in this complete position, when the ball is like upon a hill, this is a very unstable equilibrium position, because a slight shift to the ball will cause the ball to tremble down. Henceforth, it is a very unstable position of equilibrium. In the case when we were shifting the small q axially, we found that this is a stable equilibrium case, because the charge was again coming back to the center. But what if we displaced this small q equatorially? What if we displaced this small q upwards? In this way, we can find that this capital Q is repelling small q away. Similarly, this capital Q is also repelling small q away, leading to a net force in the upward direction. So this means that if in a arrangement of particles of capital Q along with small q, if you displace the small q axially, this will try to return to its original path and it will be in a stable equilibrium. But if you shift the plus q in an equatorial direction, it will keep on moving and it will go to infinity. Okay, so this is a position of unstable equilibrium. I hope this is very clear how I am trying to explain the positions axially and equatorially. When we are talking about the axial path, the axial path of displacement is a stable equilibrium one, and the equatorial path of displacement is a unstable equilibrium path. Secondly, whenever such kind of question comes, you always have to focus upon the direction of the forces, and keep this in mind. Don't make it a trend. Don't make it a trend that whenever axial displacement comes, I'm pretty sure that I will say that it is a stable equilibrium. No, don't make this a trend. It is only applicable when the arrangement is particularly like this, when there are positive charges with a positive charge in between. So this trend only applies for such arrangement. Don't make it a trend for every arrangement. Don't make it a trend that always axial displacement will be stable equilibrium and always an equatorial displacement will be an unstable equilibrium, because the moment I change the nature of these charges, these positions will swap. The axial position will become unstable and the equatorial position, displacement, will become stable. Let's see that. We will see that in the next question. So what's the further topic that we can talk about? In this particular question, we can be asked that tell us whether the movement of this particular particle is an oscillation or an SHM. So the question will specify you that the displacement is slight or a good level displacement. If the displacement is a good level displacement, keep this in mind, it will be an oscillation for sure. But if it is a slight displacement, then it will be an SHM. So I have already written this. When this small q is displaced axially, it will try to oscillate. It will start oscillating, but it can be an SHM as well. So oscillation is confirmed. Oscillation will be sure. As we know that every oscillation is SHM, but every SHM is not oscillation. As we all know that every oscillation is a SHM, but every SHM is not an oscillation. Okay, so keep this very sure. I just said it oppositely. You should rather say that every SHM is an oscillation, but every oscillation is not an SHM. Okay, I am repeating my line again. Every SHM is an oscillation, but every oscillation is not an SHM. An oscillation becomes an SHM only when the displacement is small. Okay, I am correcting myself, slip of tongue. I hope this is very clear to you. So if the displacement is very small or negligible, only then you can surely say that the path is or the motion is SHM. But if the question does not say that the displacement is small or negligible, the option that should be correctly chosen with is oscillation, that this motion is an oscillation motion or an oscillatory motion. But if the question specifies that the displacement is very small or negative, then you can if the displacement is very small or negligible, then this particular motion can be considered as an SHM. And I'm repeating again, every SHM is an oscillation, but every oscillation is not an SHM. I hope this is clear. Now let's change the nature of the charges. Once we convert the central small q into a negative one, you will find now the forces are acting in a different way, and the axial position will become an unstable one and the equatorial position becomes a stable one. The question is again asking the same pattern, find the type of equilibrium if charge is displaced axially and equatorially. So what's about axial displacement? In an axial displacement, we can find that this small q, obviously once shifted rightwards, let's shift this rightwards, we will see that this small q will be attracted towards this capital Q. No doubt this capital Q is also attracting this small q, but because we have shifted this minus q more towards the right, so the distance between these two decreased, henceforth the attractive forces between them increased. What basically will happen in such a particle arrangement, once I shift this minus q rightwards or leftwards, it will go infinitely to the left or infinitely to the right. Once I shift this particle, a minus q in between two plus q's, because both of them are attracting this minus q with an equal magnitude. So once I give it a small push, a slight push, it will shift just like a carom board. You can take an example just like a striker of a carom board. You give it a slight push, it will keep on moving in that transverse direction. So this minus q, when slightly pushed, it will leave its position, and henceforth it becomes an unstable equilibrium. And because it is an unstable equilibrium, it is not going to return back. Therefore, it is no kind of oscillation or no SHM. It is a continuous motion. It is not going to return back. So oscillations are only defined when there is a movement between the equilibrium position. Over here, this small minus q has lost its equilibrium position, and it will infinitely go to one side only. Henceforth, this is an unstable equilibrium, and you will not find any oscillation, no SHM over here. But when you push this minus q in an equatorial direction, over here you will find that this minus q is attracted backwards again by these capital Q charges. Because if you take out the electric force direction, you will see that this capital Q will attract this minus q because they are oppositely charged particles. The similar in this case, and henceforth the net force will try to keep this minus q within the loop. It will not let this minus q go outside the force, or you can say it won't allow, this force of attraction won't allow this minus q to get out of this boundary equatorially. If you shift this particular minus q axially, it will break the boundary and it will go into infinite space. But if you try to shift the minus q equatorially, this attractive forces will again push it downwards. Similarly, if you shift it downwards, it will again push it upwards, making an oscillation about the mean position. And henceforth it is a stable equilibrium. Such kind of displacement is a stable equilibrium, and it is confirm an oscillation, but it can be or cannot be an SHM. Only if the question specifies that the displacement was negligible, only then you would say that this is a SHM. Or else, if you are not specified any thing, such as it is a small displacement or negligible displacement, you are not specified anything, the only answer you have to go with is oscillation, that it is an oscillation. But if the question specifies, only if the question, I'm being very specific with my statement, only if the question specifies it is a negligible displacement, only then you have to go with SHM. If this is not specified, the only best answer that you can go with is oscillation, in spite of the fact that both will be given in the options. Oscillation will also be present there, SHM will also be present there. You have to go with oscillation. Okay. So as I have told you, that don't make it a gesture, that whenever you see an axial displacement, don't make it stable. Whenever you see an equatorial displacement, don't make it unstable. Don't make it a permanent gesture. Always be sure you equate all the forces, you see everything, you basically get a hold of the complete scenario, and then you decide whether the particle is returning back or not. If the particle returns back, yes, it is a stable. Let's say over here, if the particle returns back, yes, it is stable. But if the particle goes into infinite space and never returns back, it is unstable equilibrium, no oscillation, no SHM. I hope this is very clear to you guys. Moving on to another arrangement. This is a good kind of question. A very helpful concept will be found from here. We have an arrangement of plus q at a and minus a on the y-axis. I hope you are seeing the graph over here. I don't need to explain it further. Secondly, a small minus q is placed at 2a position on the x-axis. So obviously, from the first instant, we can find that these are 2 point charges. So obviously, they are static. There is no motion initially. Henceforth, Coulomb's law is going to be applicable. No induction over here because these are 2 point charges, and 2 point charges will never induce anything. Okay. So the first thing by seeing this question is that very clear that Coulomb's law is being applicable over here. Because this is minus, this is plus, obviously there will be a force of attraction towards, and similarly there will be a force of attraction towards. Means both of these particles are trying to get a hold of each other. Henceforth, if you place a minus q and this minus q is free to move, this minus q will actually start moving towards the center. And because as it reaches the center, it has attained some kinetic energy because of the motion, it will move further away. But when you take the minus q over here, now the attractive forces will be in this direction, causing the particle again to return back at the central position. And because this particle, while returning back, again has some velocity, it will again move further away. And as it moves away, again it will get attracted, and henceforth this creates a oscillatory path about a mean position from the origin. Henceforth, the question asks, if the minus q is free to move and is released, then what will happen in this particular case? And because we can find by the directions of force, you always have to equate with the direction. You always have to draw the direction in such kind of question, whether to find whether the particle will oscillate or will have no movement or whatsoever, or whether it is unstable or an unstable equilibrium. You always have to make sure you have to draw the directions of electric forces, whether it is repelling each other or whether it is attracting each other. Only that will help you find whether it's stable or unstable. Now, because this minus q is returning back always to the mean position, this is a stable equilibrium. So we can say that this particular motion is a stable equilibrium. Yes or no? We can actually say that this particular motion, or it would be more correct to say that this particular particle is at a stable equilibrium or in a stable equilibrium, right? Henceforth, because the particle is in stable equilibrium, it will oscillate. Displacement is large. The question has not mentioned about displacement. It is not saying that the displacement is small or negligible. You can also see that this small q minus q was placed at 2a distance. So obviously 2a distance is not a negligible distance or a displacement. So make sure always you have to go with oscillation until and unless the question specifies it is a very negligible displacement, or by seeing the diagram you can guess it out that yes, it is a very small displacement. Over here I can clearly see that the displacement is large enough, it is a bigger length, the displacement is not small enough to call it an SHM. Henceforth my final answer would be oscillation and not SHM. So this is an oscillation, displacement is large as we can clearly see from the diagram, and only when displacement is negligible, only then it is SHM. What about SHM? What if the particle would be doing an SHM path, or let me say it in this manner, that what would happen if the particle were doing an SHM path? If SHM would be included in the question, then there is a high probability you will be asked the time period of the SHM. Let me repeat my word. Be very specific with this. This kind of questions will turn your head around. If such kind of a question comes in electrostats chapter, it will be a no ball for you. If you want to solve such kind of question, first of all you have to find you must be knowing with the equation of SHM, and in the question also you have to find the equation of SHM. I will be solving two particular examples which will help you find how to solve such kind of patterned questions where the SHM, where the particle is doing SHM and the question is asking to find the time period of the SHM. In this particular case, the equation of SHM should be thoroughly revised. So I have written already, the equation of SHM is somewhat like this. This is the acceleration. The double differentiation form of displacement, d square x by dt square, is none other than but acceleration, plus omega square x equals 0. X is, you can say, the distance that we will be given in the question. Omega, that's the angular velocity, and by this you will find the omega, and after that you will have to place this omega in the formula 2 pi by omega for the time period of the SHM. So the time period of the SHM, if asked, will be calculated by t equals 2 pi by omega, and you have to equate the force ma with this particular relation m d square x by dt square, because you can obviously convert a into d square x by dt square. So the electrical force will be equated with this particular equation, and from there you have to find the d square x by dt square. In this relation, you actually have to focus upon d square x by dt square. Once you get the value of d square x by dt square, now it becomes a very easy game. All you have to do is equate the electrical force between these particles. Let's say this is the question, and in this particular question we were asked to find this minus to find the time period of this minus q, and the displacement were said to be very negligible. Let's say it was not given 2a, but it was said that the displacement is very less. It was like displaced from here to here, displaced from here to here. So the displacement is very less, you can neglect it. In that case, how to calculate the time period? This becomes a good question. And this is actually a question kind of mains level or advanced level question, which can be sometimes asked in NEET. So over here we have completed our equilibrium position, and literally trust me when I say it is very tough to teach in English. Very tough. Because English is not my native language and I am not used to speak it every time. It was our school days only when used to speak or talk in English like this. It is a very tough job to teach in English. Trust me. I hope this is clear, and we will work on this. Just wait a second. We will be continuing the class. Let's focus on the module. Wrong one. Okay. Most welcome, most welcome. Without any further delay, we have already completed up till where? We have completed about this. We have completed the golden key points. There was nothing left. Illustrations have been completed. The beginner boxes have been done. I hope you are doing with all this. You're not leaving it. Let's focus on the Coulomb's law. What's written in the module? Let's get to it line by line. Let's see what's written with the Coulomb's law. So Coulomb's law that we have already said is strictly applicable on point charges. Focus on static point charges. Or you can even apply Coulomb's law on spherical conductors, but they should be far apart. So the electric forces of interaction between two static point electrical charges, keep this word in focus, static. The point charges should be static in nature. Okay, make this very clear. Secondly, two static point electrical charges is directly proportional to the product of the charges, exactly, and inversely proportional to the square of the distance between them, and acts along the straight line joining the two charges. So these forces are always acting along the line, that line which joins the charges. The force is acting always along that. Consider two point charges q1, q2 separated by distance r. Let F be the electrostatic force between these two charges. According to Coulomb's law, F will be directly proportional to the magnitude of these charges and the inverse square ratio. This particular inverse square law, this particular relation, F is directly proportional to 1 by r square, or you can say F is inversely proportional to r square, is specifically named as inverse square law. We will talk about this in the further topic. So the expression comes out to be F electrical force, Coulomb's force, equals k q1 q2 by r square, where q1 and q2 will be written in magnitude wise, because over here we are not dealing about vector product. So because vector sign is not included, we have nothing to do with sign. Only the only thing that we'll be seeing here is magnitude. We are given the value of k, 9 into 10 to the power 9. Keep this very clear. 9 into 10 to the power 9 is the value in MKS. If the option or the answer or the question says to find it in CGS, then k should be taken as 1. K is the Coulomb's constant or electrostatic force constant. Coulomb's law in a vector form, as we have discussed earlier. F vector, forget this 2 1 1 2, you don't have to keep this in mind. These will only confuse you. So don't remember this F vector 2 1, F vector 1 2. I know these are kind of handy things, because F1 2 means force on 1 due to 2. You can actually know about the relation. It is important to know about the relation. What if the question says F12? If you don't know the meaning of F12, you won't be able to evaluate the answer. So keep this very clear. If such kind of a pattern comes in the question, you just have to keep in mind. Don't remember this in the formula. You don't have to remember F21 is such kind of a relation. No, forget this. You only understand if force is written like this, 1, 2. What does this mean? So that it will help you in finding the answer correctly. So it means force on Q1 due to Q2. That's it. Means force on 1 due to 2. Here, therefore 1, 2. That's it. Nothing more than that. The only vector form that you have to remember is F vector equals k q1 q2 by r square. That's the magnitude with r cap. And when you abbreviate the r cap, so r cap elaborates to r vector by r magnitude. Henceforth, the final relation that we have already discussed comes out to be F vector equals K Q1 Q2, and this time you have to use the sign, by R vector magnitude. Don't get confused by this relation. It is just a confusing pattern. You will only get confused. Only remember the important thing. F vector equals K Q1 Q2 with sign divided by the magnitude of the R vector, magnitude, only the magnitude, that also to the power of 3. So R cube times R vector, and R vector has to be calculated in this particular order. Target जिस पर फोर्स स्टडी कर रहे हैं, दैट मीन्स द चार्ज ऑन विच यू आर स्टडिंग द फोर्स, or that is asked in the question, minus the charge that is applying the force, r vector of the source, जो force लगा रहा है. Okay, so the particle that applies the force is the r source, and r target is the position vector of that particle on which you are studying the Coulomb's force, or on which particle it is asked by the question. Let's say there are two particles Q1 Q2, and the question says find the force on Q2. So Q2 becomes the target and the force is being applied by Q1, so Q1 becomes the source. I hope this is very clear. Okay, no doubt with this. So this is the complete force, Coulomb's force, in a vector format where Q1 and Q2 has to be used with sign. Principle of superposition, we have discussed this earlier. Coulomb's force is a two-body interaction implying that electrical force between 2 point charges is independent. Particularly see the line. Superposition is applicable where 2 point charges, or the force between 2 point charges, is independent of the presence or absence of any other charge. That means if two charged particles are present close to each other, they will apply the same amount of force to each other irrespective of the presence of any third charge in the environment. No doubt the third charge will also interact with them, but when you are focusing on two charges, the only thing that will be applicable is the force between those two charges. You don't have to worry about the third charge. Yes, the third charge will also individually apply another electrical force on the charges, but in that scenario also, if you are considering the third charge with any other charge, then just make it a sense that those two charges now will become an individual pair, and now the third particle will be out of the field or out of the picture. I hope this is clear. So when you are just seeing 2 point charges, irrespective of anything else, you don't have to focus on anything. The only thing that you have to focus on is those two charges. Henceforth, superposition is applicable. And when you have the complete component of all the forces on one charge, you have to vector sum that. You have to get the vector resultant, and you will get the net force on that particular charge. So that is how the principle of superposition work. And by this principle of superposition, we actually came out on the topic of, or we discovered the topic of equilibrium of 3 point charges. Because in the equilibrium of 3 point charges, we're actually dealing with the superposition. Because without superposition, you cannot find equilibrium position. And because we know the tips and tricks of how to find the equilibrium position, it is easy for us. We don't have to calculate the net force always, every time, for every question. We don't have to do that. Let's see what the equilibrium of charged particles has to say. Then we will solve some questions as well, important questions and SHM questions. Very important for that. Keep this clear. Equilibrium of charged particles, what is it? In equilibrium, the net electrical force on every charged particle is 0. So this is actually talking about the equilibrium of the system. This is actually talking about the equilibrium of the system, because it is the system's equilibrium only when the force on every particle is 0. But if it were the equilibrium of a single particle, then only the net force on that single particle will be 0. But when I say the net force on all the particles is 0, that means it is the equilibrium of the complete system as a whole, including that particle. The equilibrium of a charged particle under the action of Coulombian forces alone can never be stable. Now, what this line means, this is a very important line. This might confuse you at times if you don't understand this properly. What is this line saying? Read it once again, then I will make it clear to you. The equilibrium of charged particles under the action of Coulombian forces alone can never be stable. That means if you have only two charged particles, let's say plus q or plus q minus q, alone these two charged particles can never be at equilibrium, because if there is no third charge to balance their net forces, they will always start moving either away from each other or towards each other. If you have only two charges, let's say plus q, they will start repelling each other and they will start moving away from each other. Only two charges can never be at equilibrium, irrespective whatever their sign is. Let's say it is plus q minus q. Plus q minus q will never be at equilibrium alone. They will start attracting each other. They will start moving towards the center. I hope this is very clear. So, equilibrium of a charged particle under the action of Coulombian force alone can never be stable. You have to keep this in mind. Because a Coulombian force alone can never stabilize a particle. You need something else as well to stabilize that particle. Rather, I should say this complete statement in a more defined way or in a more proper way. If a complete system has only Coulombian forces between them, then the complete system won't be stable enough always, because a slight displacement can cause oscillations or SHMs. I'm repeating my word. If a system is only under Coulombian forces, there is always a probability that a slight displacement can initiate oscillations or SHMs. So now the question that might appear in your mind is, so what about if we want a particle to be in equilibrium, then what kind of forces should we additionally apply? So in this case, we can say that the weight can be a very good example. Sometimes you have been asked a question that there is a parallel plate capacitor which is placed like this, but I'm showing you like this. A parallel plate capacitor which has a uniform electric field between the plates. And you have to place an electron such way that it is stable, it is not moving. In that case, what we do is that we equate the mg of the electron with the electrical force. And we say that the electron is at equilibrium because the weight of the electron balances the electrical force. But what if we say that forget about the mass of the electron? So there is no other force to balance out the electrical force. Henceforth, I'm making it very clear and I'm concising the statement once again that if charged particles are under only Coulombian forces alone means that only Coulombian forces, then that charged particle can never be unstable. When you say 100% stability, that can never be achieved. So there are always chances that a small disturbance will lead to oscillation or SHM. So complete stability can never be obtained just by Coulombian force. So I am repeating the line again once and for all. I hope this is very clear. The equilibrium of a charged particle under the action of Coulombian force alone, can never be stable. Okay, because upon disturbance, oscillation will occur and even SHM can occur if the displacement is small. Now, as we have already discussed, two charged particles must be like in nature so that this particular question we have already discussed how to do or how to take approach for that. So two charges must be like in nature. So in that case, if the two charges are like in nature, you will have to equate the forces. Then again, the second statement says that the third charge should be unlike in nature. That means when you have a 3-point charge system and you want the 3-point charge to be in equilibrium, what the required condition is, these terminal charges should be like in nature. And the third charge that you introduced between them should be unlike in nature. And over here also, they have equated the forces that we have also done. So we are not going to repeat this once again. Rather than, we will be focusing on the formula. And the same formula has been written over here. What we will be focusing on is the Q1 and small x. Because in the formula, we have to be very specific with Q1 and x. So the distance is x from Q1 of the particle small q. And this x can be written as under root Q1. Be specific with Q1. This x can be written as under root Q1 by under root Q1 plus under root Q2 times small r. And the small q that is placed between these two charges is minus Q1 Q2 divided by under root Q1 plus under root Q2 whole square. Now there are some applications with this formula. You have to apply this particular formula only when x resides between Q1 and Q2. If there is a scenario where this x is coming outwards, that means, I mean to say, when the equilibrium position is lying between these two charges, only then you can apply this formula. If the equilibrium position is not present between these two charges, if the equilibrium position is lying outwards these two charges, in that case you have to again vector sum the forces and you have to equate it to 0 to find the equilibrium position. That we know already. That is not a big task to do. But remembering the formula will always help you, because most of the chances are there that the examiner will ask you a pattern like this, where the equilibrium position will lie between the two terminal charges, and you will get a direct relation. You will get a direct answer from this formula. X equals under root q1 divided by under root q1 plus under root q2 times r, and the value of this small q that was placed in between is minus q1 q2 divided by under root q1 plus under root q2 whole square. This particular formula will hardly take you 2 to 3 times of revision, and you will get to it. You will get a command on this. And obviously, we will make sure that while using Q1, Q2, we will use the sign. Okay, so this particular formula will also tell you the neutral point, that is the point where force is 0 as well as where the electric field is 0. So this tells you two positions, the position of 0 net force and the position of 0 electric field. So you can apply the same formula for both the type of questions. What kind of question? I'm telling you, just get a look over it. Sometimes a question would ask that there are two charges Q1, Q2. So we are placing a third charge between them. So what should be the position of that third charge to have a net force of 0? So you can apply the same formula. Or the question can be asked in such a way that there are 2 point charges Q1 and Q2. In between them, at which position the electric field due to both of them will be 0? So similarly, where the electric field is 0, the force is 0. Henceforth, that is actually equilibrium position, the same thing. So if the question asks the net force is 0, that is equilibrium. Electric field is 0, that is also equilibrium. So you can apply the formula for both the things. You can either find the 0 force through this formula, or you can find the position of 0 electric field again by the same formula. And small q equals minus q1 q2 divided by under root q1 plus under root q2 whole square. Now, I have written the marked dimensions of an equilateral triangle. This will be very helpful for you in the future reference cases, because you will be asked to find potential energy of such triangular systems of charges. You will be asked to find the potential of such triangular system of charges. So you must be very clear with the distances of all the ends. So the complete straight line that starts from the vertex to the mid of a baseline. So this complete line is the median, that's root 3 x by 2. Let's say the side is x. So the complete length of the median comes out to be root 3 x by 2, and the distance from the vertex to the centroid is x by root 3, and the distance from the centroid to the midline of the bottom base, that is x by 2 root 3. So it's x by root 3 and this is x by 2 root 3. I know this might be confusing, but you have to revise this multiple times to get a hold of it. If you don't revise this, there will be problem faced by you in questions of potential energy calculations and in the further questions of this chapter. Now, over here, this particular topic is discussing about the equilibrium of symmetrical geometrical point charged systems. We have already discussed about this, that if similar charges are placed at the corners or the vertex of a regular polygon, the central position is the point of equilibrium. And what shall be the charge of this centrally located charge? Or you can say, what shall be the nature and magnitude of this centrally located charge? So there are formulas for that too, but I would say you don't need to remember this. It would be better if you equate the forces, but still, if you can remember them. There's no big deal for that, because there are many times that such questions are being asked and the direct formula will give you relief. If you remember the formula, you will get the direct answer. You don't have to even do any calculation. So value of q at the center for which the system remains in equilibrium, because we are actually concerned with finding the equilibrium of the complete system and not that of the particle, because the particle can be of any nature. It can be of plus q, it can be minus q, for the particles equilibrium to be there, but we want the complete system to be in equilibrium. So for that, the charge of the nature of this capital Q should be very crucial. That should be very specific. So for capital Q that is placed at the center to be at equilibrium, any value of this Q will work. Even a positive Q will be at equilibrium at the center of this polygon, and even a negative Q will be at equilibrium at the center of this polygon. Okay, I have just extracted the main value, that is the distance of the vertex from the centroid. So this distance is particularly, most of the cases it is useful for us, that's x by root 3. We have discussed this earlier as well, and I have written this once again so that it becomes a multiple time revision segment for you. So in a triangular case, if small q charges are placed at the vertex of a triangle and you are placing a small q at the center of the triangle, and you want that the complete system should be in equilibrium, in this case q equals minus q by root 3, and this q is the particle placed at the center. Don't confuse it with the particles at the vertex. Please keep this in mind. This q is actually saying about the particle at the center, equals minus q by root 3. And for such a situation, the particle q should be, for the system's equilibrium, this particle q should be minus q bracket, whole bracket, 2 root 2 plus 1 by 4. If it is not too much for you, you can remember them. But if you say that, sir, these all formulas are too much for me, I have already worked so hard to remember them, I cannot remember these two, no problem with that. You can always vector sum the forces and you can equate them. You will again get the same answer. So you don't have to worry for that. If you vector sum the forces, you will again get the same thing. Don't worry for that. Similarly for a square, if you vector sum the forces, one acting in this way, one acting in this way, one diagonally opposite, and one should be balanced with this. So I hope you're getting my point, what I'm trying to say. So there is no necessary condition, but this you should be remembered with this, because in such questions, trust me when I say, if you don't remember the formula, it will be very tough for you to find the equilibrium position. I know it's not impossible, you can do this, but it will take time, it can lead to confusion, and it can lead to similar options, and your answer might fluctuate between two options. So please, I'm being very specific, please remember these two formulas anyhow, but these two can be calculated out at the exam center, but still if you remember them, that's very good, that's very fantastic, there's no issue for that. Okay, so let's repeat the formula again. X equals under root x1 divided by under root x1 plus under root x2 times r. R is the complete distance between q and q2, and the value of small q should be, that is between them, should be minus q1 q2, no under root over here, no under root over here, minus q1 q2 with sign, divided by under root q1 plus under root q2 whole square. No squaring over here, under root over here, no under root over here. Okay, be specific with the formulas. Now, this pendulum case we have already done. This module is particularly discussing about the same pendulum case that we have briefed about earlier. Equilibrium of suspended point charged system. As you can see over here, the tension is componented as T cos theta and T sin theta. T sin theta is equated with the electrical force of repulsion between the two balls, and T cos theta is equated with the mg. And because of these two equations, we got tan theta as Fe by mg. And when you elaborate Fe, mg remains the same in the formula, but Fe becomes kq square by x square because the distance between the balls are x. So Fe becomes kq square by x square. Henceforth, the relation of tan theta comes out to be kq square by x square mg. And if theta is small, you can say that tan theta is equal to sin theta, that is equals to theta, that's x by 2l. And there can be multiple variations of this particular question that we have discussed in the previous lecture. I'm not going brief into that. So if the whole setup is taken into an artificial satellite, we know that g effective becomes 0, so the mg is lost. There is no mg, and both of the balls will go farther apart. The distance between the balls will be like 2l. The angle between them is 180 degrees. We can derive it. Yes, obviously we can derive it, but as I said, in exam, derivation won't help you. You have to save time. You have to complete a question within 15 seconds, 20 seconds. So if you start deriving a question at the exam center, so you are not giving a board paper. Okay, board exams are all about derivations, but MCQ exams and competitive exams is all about smart work. So if you have remembered all the formulas, it will be an easy game for you. And no doubt we can derive for that. Physics is a very vast topic. There is no doubt for that. Now let's get a control over the golden key points. What are the points that we have to discuss over here? So the first point that comes into play is Coulomb's law, which is a physical law and it can't be proved. If you are having a doubt with this line, I have already said it in my lecture that the laws of physics cannot be proved. They are just based on some observations or some experiments. So Coulomb's law is also a physical law and it cannot be proved. Okay, so Coulomb's law is a physical law. It can't be proved, and this Coulomb's law is based on physical observations and is not logically derivable from any other concept. That is what I was trying to say. Now experiments reveal its universal nature till today. Yes, so we are only getting Coulomb's law from experiments. There is nothing for to prove in it. Now, the law is analogous to Newton's law of gravitation exactly. So this gravitational formula, force of gravitation F equals to G m1 m2 by r square, is very much similar to Coulomb's law, and with the difference that electrical force between charged particles is much stronger than gravitational force. You must be knowing that the gravitational force is the weakest force among all. The gravitational force is the weakest fundamental force among all. Secondly, the electrical force is very, very stronger than the gravitational force. Consequently, Fg is neglected when both Fe and Fg are present. Yes, so there are scenarios when you have to neglect Fg. Sometimes it will be asked in a question that two particles have a mass as well as charge. So there are times when you have to neglect the gravitational force of attraction between them to get the answer correctly. But if the question demands that you have to use G, then you have to consider the gravitational force of attraction as well. The biggest difference between them is, the one difference is that they are smaller, one is larger in magnitude, means the gravitational force is very weak and the electrical force is very strong, not much strong but strong enough than the gravitational force. But one major difference is the gravitational force is always attractive in nature, but the electrical force can be dual. It can be attractive as well as repulsive. So the electrical force can be attractive or repulsive, while gravitational force is always attractive. Keep this in mind. Two mass particles will never repel each other. Two mass containing particles, due to gravitational force, will never repel each other. They will always attract. So gravitational force is always an attractive force, never repulsive. Secondly, the electrical force depends upon the nature of medium between the charges, but gravitational force does not depend upon the nature of the medium between the mass particles. But the electrical force will depend upon what dielectric is placed between the charges, or what the medium is. The force is conservative, exactly, that is, work done in moving a point charge around a closed path under the action of Coulomb force is 0. It's a conservative force because it depends only upon the initial and final position, not on the path. So whatever your path is, it does not matter. The only thing that matters for a conservative field is the initial and the final position. And for a conservative field or a conservative force, the work done in a closed loop is 0. Now, this law expresses the force between 2 point charges at rest. I have already made this clear that Coulomb's law was applicable when 2 point electrical charges are static, and this point makes my already discussed statement reappear once again. So the concept is again reappearing. The law expresses the force between 2 point charges at rest. So Coulomb's law is actually devised for 2 point charges which are at rest. They are not moving along. They are at rest. Only at rest we can perfectly define the Coulomb's law of force. So at rest, in applying it to the case of extended bodies of finite size, care should be taken in assuming the whole charge of a body to be concentrated at its center, as this is true only for spherically charged bodies, that too for external points. What this particular statement is trying to say, that when you are applying Coulomb's force on extended bodies, in this particular case, you cannot compare the complete length as in Coulomb's force. What you have to do, you have to assume that the complete charge is confined at a position, and then you have to treat that complete infinite length as a point charge, and then you can actually carry out the Coulomb's law. So for Coulomb's law, you have to keep sure that whatever particles you are comparing, that should be point charges or should be considered as point charges. Similarly, for spheres, you can consider that the two spheres in attraction or repulsion to each other. In the case of spheres, yes, Coulomb's force will be applicable, but there are different scenarios where induction can lead to different answers. We will get to that as well. Now, electrical force, this can become an assertion reason type question. Many times physics have statement like questions, so this can become an assertion reason like question. Read this line carefully. Assertion reason can be asked from this line. Electrical force between two charges does not depend upon the neighboring charges, and therefore superposition is valid. The concept of superposition is only valid when the electrical force between two charges does not depend upon the neighboring charges. And this can become an assertion and the reason. So let's say the assertion can be that the concept of superposition is valid in Coulomb's law. This can be the assertion. What shall be the correct reason for this particular statement? The correct reason is because electrical force between two charges does not depend upon the neighboring charge or the third charge, and this is the reason why superposition is valid. Okay, so I hope this is very clear. We have discussed this earlier as well. The net Coulomb's force between two charged particles in free space and in infinitely extending medium R. So how can you relate both of these? So in free space, F equals 1 by 4 pi epsilon naught, that is the permittivity of the vacuum, Q1 Q2 by R square. But in a medium, this epsilon naught becomes epsilon, that is absolute permittivity of the medium, and this absolute permittivity of the medium is equals epsilon naught times epsilon r. So the formula will be like 1 by 4 pi. Instead of absolute permittivity, you will write 1 by 4 pi epsilon naught epsilon r times q1 q2 by r square. So that will be the new force in the medium. And as we have discussed in our notes, that if the question says there was a particular type of question that comes very easily, it is asked. Let me show it to you once again so that you can get a hold of it. The multiple times you see a concept, the more better it places its position into your head. So if the force in the air and the force in the medium are same, then what shall be the relation of the distance between the particles? So the relation comes out to be the distance in the air, r air, equals under root epsilon r times the r in the medium. Okay, so r air equals under root epsilon r times the r medium. I hope this relation will be clear to you, and it can be evaluated by this particular concept that I have shown over here. I just replaced epsilon naught with epsilon naught epsilon r. This epsilon r represents the relative permittivity of the medium. Okay, so that's the relative, that is dimensionless and unitless. This is epsilon r, that's relative, not absolute. And this can also be called as a dielectric constant of the medium. Okay, so this is r air equals under root epsilon r times r medium, and henceforth the distance in the air will be greater than the distance in the medium. Okay, so the same thing is explained over here. I have written the same thing over here. Now the last 2 points are very crucial. Keep this very clear and very important. These two lines are: dielectric constant K of a medium is numerically equal to the ratio of the force on 2 point charges in free space to that in the medium extending infinitely. That means this formula is said in the terms of statement: dielectric constant of a medium is numerically equal to the ratio of the force on 2 point charges in free space to that in the medium. Dielectric constant equals the ratio of the forces in free space to that in the medium. So dielectric constant equals F in air divided by F in the medium. Now this last line is very important. Although the net electrical force on both particles change in the presence of dielectric, but force due to one charged particle on another charged particle does not depend upon the medium between them. I would want you to read this line once again. If you're seeing the lecture sincerely, I want you to read this line again and try to understand. First, read it once again with your wit and try to explain this within yourself. I will surely explain it to you what this line wants to say. If you were able to understand, well and good. If not, listen. Read the statement once again. What is the statement saying? The statement says, although the net electrical force on both particles change in the presence of dielectric, net electrical force, but force, not net. Net electrical force changes in the presence of dielectric, but force due to one charged particle on another charged particle does not depend on the medium between them. What does this mean? Because from time immemorial, we have been knowing that whenever a dielectric introduced, the force changes. The force becomes times dielectric. So what's the point in saying this? That the net electrical force depends, but the force does not depend. To be very honest, this particular line is not 100% correct, but conceptually it will teach you something. I'm again telling you, this particular line is not 100% correct. It is a flawed kind of statement, but you can say that this line will teach you something. The thing is, listen to this. When you have a point charge, the first thing that you have to keep in mind that point charge can cause induction. Do you agree with this? Yes, sir, I agree with this. Now, if you have 2 point charges plus q and minus q placed at a particular distance, and you introduce a dielectric between them, and the dielectric constant is k, let's say. So because these point charges have the power to induce opposite charges, so what this plus q will do will induce minus q in this side of the dielectric, and this minus q will induce plus q at this side of the dielectric. Now this induced charges will set an electric field in the opposite direction to the force between these two charges. Now listen to my word clearly. Whenever you place a dielectric between two charges, this plus q never stopped applying force lesser. Initially, this plus q was applying force or was getting the force k q1 q2 by r square. Similarly, this minus q was also giving an action reaction force of k q1 q2 by r square. But when you introduced a dielectric medium, because of the induced charges, there was an opposite force applied in an opposite direction, which led to the decrease in the net force. But this plus q never stopped applying the same amount of force. Even after placing a dielectric, the force applied by this plus q was k q1 q2 by r square. But because this dielectric also applies a force in opposite direction, or you can say also sets an electric field in the opposite direction, because of these induced charges, the force applied by this plus q overall gets decreased, or we see that the force is being decreased, but this plus q is trying its best to maintain the force. But this dielectric, because it sets an electric field in an opposite direction, which sets an opposite electric field, because of this the force between them is being opposed, hence the net force decreases. But you have to keep this in mind, the force due to one charged particle on another does not depend upon the medium. You try to understand this phenomena something like this. There are two people that are trying to pull each other with the same force. Let's say this is pulling this one with 10 Newton, similarly this is pulling that one with 10 Newton. So these two people are pulling each other with the 10 Newton force. They are applying same force on each other. What happens is a third particle comes in between and disturbs their force. So was it that this person stopped applying 10 Newton? So you would say no, this person was applying 10 Newton as always. Similarly, this person was also applying 10 Newton as always. But because of the introduction of a third party, a disturbing party, this party did what? It disturbed the net force between them. So this particle is applying 10 Newton with its full potential. But what happens is the disturbing party reduces the net force. So to us, it appears like the force has reduced because of the introduction of this particle. But these particles never stopped applying the initial force. Today also, even after placing the dielectric between them, the forces are still 10 Newton and 10 Newton. But because of this dielectric, the overall net force reduced. And why did such happen? Because the dielectric got induced charges. Because of the presence of induced charges on the dielectric, this dielectric tried to reduce the overall net force. But these two particles were still trying their best. They were still trying their best to apply the force at the equal level. Henceforth, the line says, although, please see this clearly, although the net electrical force on both particles change in the presence of dielectric, the net electrical force do change in the presence of dielectric, but the force applied by both the particles does not change or does not depend upon the medium between them. And why does this change in net force occurs? Because of the polarization present in the dielectric. Because of the inducement of charges, the dielectric got polarized, and because of the polarization, this polarization of the dielectric in the presence of these point charges, or because of the phenomenon of induction, this dielectric will set an electric field that opposes the net electrical force, and henceforth the net force decreases, but the initial force between the two charges was always the same, and it does not depend upon the dielectric medium. Okay, that is, polarizing behavior of a dielectric placed between 2 point charges means the complete phenomena occurs because the polarization of the dielectric happens. Because the dielectric becomes polarized, this polarized dielectric opposes the electrical force, and the net electrical force decreases. I hope this is very clear to you. Now we have some examples and the most crucial question that we were waiting for, the question of SHM. This kind of question has been done. The question says 2 point charges are replaced by spheres. What shall be the further commentation of the force of repulsion? So obviously, because the distance increases, the force of repulsion decreases. That's a very easy question. Now you have a question that for the system shown in figure, this system, find Q for which the resultant force on small q is 0. So this small q is placed at the corner and you have to find any value of capital Q. So these are small q's placed at the diagonally opposite corners and these are capital Q's. So what you have to do is you just grab one charge small q and make the net force 0 on it, because the question says the resultant force on small q is 0. So what you have to do, you grab this small q, you find all the forces acting on this small q and make it net 0. You will get the answer. One question, very good question, that's a very conceptual question. Read this question. 5 point charges, each of value plus q, are placed at the 5 vertices of a hexagon. So this hexagon has 6 corners, but we are placing 5 charges at 5 corners. The 6th corner is left as it is, no charge over there. The side is L. Of every side of the hexagon is L. Now what is the magnitude of the force on a point charge of value minus q placed at the center of the hexagon? So we are not going to look at the solution. We are going to build an approach on our own. What shall be the approach? What should be the approach? In seeing this particular question, what we can approach over here is, we are placing a minus q at the center and there are 5 plus q charges at 5 different corners. And the central charge is minus q. There is no charge at A. So the one way to solve this is the easiest way I would say. The easiest way to solve this particular question is by making all the vector summation of the forces. You can find that this small q will be attracted by the force at F, the charge at F. Similarly, this charge at C will also attract this minus q from the center. Henceforth, these two forces will cancel out. So you can do this in your mind that these two forces cancel each other. Similarly, this minus q charge at the center will be attracted by the charge at E and it will be attracted by the charge at B, and these two will also cancel out each other. Henceforth, the only net force applicable on this minus q at the center will be by the charge at D. The charge at D, that is small q, will attract this minus q, and because the length is L and in a hexagon all the triangles are equatorial, the distance is also L. So hence the question asks, what is the magnitude of force on point charge value minus q? So the magnitude of force will be very easy. I can say it by without writing as well. K q1 q2, that is q square, kq square by L square. So the final answer should be kq square by L square, and because the question asks magnitude, I have no relation with the sign. Okay, so I will only say or tell about the magnitude. But this question teaches you another method of solving the problem. What I said was a last, or you can say the easiest retort. You can do that anyway, any day. It is very easy for you to do. But when you have such kind of a question, you have to learn a different pattern also, because these kind of missing charges will be helpful for you to evaluate questions of electric field or electric potential. There are possibilities that such kind of questions reappear with a different approach but with the same concept in the topics of electric field and electric potential. So what we have to do over here is we have to take the complete system as one and we have to reimagine the system. Let's say if there were a charge at capital A. Let's imagine if there were a charge at capital A. So that makes it, as we place a charge small q at A, it will make the force at minus q 0. Yes or no? Obviously. So we can derive an equation from this. You have to read this statement once before we come to the final conclusion. If there had been a 6th charge plus q at the vacant vertex of hexagon, then force due to all the 6 charges on minus q at O would have been 0, as the forces forming a pair due to charges lying opposite to each other will balance each other. Exactly. Let's say now we are assigning some terms to the forces. So if F vector is the force due to the 6th charge and F vector is due to the remaining 5 charges, I'm reading this once again. If F vector, small f vector, is the force due to the sixth charge that would have been placed at A, and capital F vector is due to the remaining 5 charges. So we can say that capital F vector, that is the force due to the 5 charges, plus the force due to this small charge will be equals to 0. So I can say capital F vector plus small f vector equals 0. That means the capital F vector equals minus f vector, that is the vector form. So we will be specific with the sign plus and minus. But we are comparing the magnitude. So just we said that the force applied by all these 5 particles will be equal to the force applied by this imaginary sixth particle. And this particular question does the same thing that we did earlier, that cancelling out the forces of these particles and evaluating this force only. This question does the same thing, and the answer comes out to be kq square by L square. Obviously it has converted k into 1 by 4 pi epsilon naught, but I am telling it in a simpler way, kq square by L square. So hence this particular kind of question can be solved with 2 approaches. One approach can be you cancel out the equal and opposite forces and just evaluate the one force which is not being cancelled out by any other force. So that would also give us the correct answer. Or you can actually consider or assume an imaginary particle at this point A and assume that all the net forces will evaluate to 0, and you can evaluate it in this form. Both of the forms are correct. Both of the forms should be known by you. You should have the knowledge of both the categories of solution, because knowing a question by multiple solution ways will help you build a command over the topic, because such kind of solution will be helpful in further topics. Okay, so every question should be solved or should have multiple variants of solution, and you should be known with all the variants of solution to get a better grip on the topic. Now comes the most important question, that is this question have been arrived in JEE Advanced and can appear in NEET as well, and it can appear in your test series. So I will give you a better approach of how to solve this question. Remember we discussed about the equation of SHM. See to this. This is a very important topic and this is a very important question as well. I will remove the module for a second and I will focus something over here. We were known with the equation of SHM that was somewhat like d square x by dt square plus omega square x equals 0. This was the equation of SHM, and I already told you that if there is a 3 particle system, there are chances that the question can ask you the time period of the oscillating particle. I have already discussed that whenever a particle is shifted axially or equatorially, it can lead to different situations. It can lead to stable or unstable equilibrium, or it can lead to, if you say, SHM or oscillation. But if the question says, now let's read the question and solve it properly without seeing the solution. Now let's read the question. I will help you build the approach. Just by the equation of SHM that I just wrote there, you will have a better grab of the answer. 2 charges, each of magnitude q, are fixed at 2a distance apart, and a third charge small q of mass m. So we will neglect gravitational force of attraction over here. Charge q of mass m is placed at the midpoint of the line joining the 2 charges. Okay, you got an image. We will draw that over there as well. All charges being of the same sign. Okay, fine. If q charge is slightly displaced from its position along the line, that is axially, and released, then determine its time period. If you want, you can pause the video. You can read the question once again. But because I have understood the question, I will directly move on to the solution. So I remove the module now and I will solve it over here. Now let's see what is it saying. Now the question said that there are 2 capital Q charges which are at a distance 2a, and we have a small q at the center, and all of these 3 charges have the same sign, plus plus plus. The third charge which has a mass m as well, but this mass will not lead to any kind of gravitational attraction because we will neglect gravitational attraction. Now if charge is slightly displaced in the axial position, so first you have to find whether it is a position of stable equilibrium or unstable equilibrium? I have already told you, because this capital Q will repel this small q, this capital Q will also repel this small q. So once you displace this small q a little bit to rightwards or leftwards, whatever you do, so you will find that this small q will be repelled more by this rightwards capital. So this capital Q will repel it more towards the left, and this capital Q will repel it less towards the right. Henceforth, this small q will have a tendency to again reach the center. And obviously we know that this will lead to oscillation, because this is a position of stable equilibrium and it is displaced axially. So this is the stable equilibrium, and the small q particle will again try to reach the mean position. And because the question clearly states that the displacement is very small, so this oscillation is particularly SHM, and we have been asked to find the time period of this particular oscillation. Do we know the formula of time period? See, I will make this question very easy for you. You might be thinking that this is a very tough question to solve, or whenever such kind of question comes, you guys are like stuck in between, you don't know what to do. So there are some basic approaches to solve any question. The basic approach is over here. You must be familiar with the equation of SHM. This is the standard equation of SHM, that is d square x by dt square plus omega square x equals 0. Secondly, you must be knowing the formula of time period, that is t equals 2 pi by omega. Omega, that's angular velocity. Okay, angular frequency whatsoever, angular frequency, sorry, t equals to 2 pi by omega. Okay, now what should be the next approach? Find the forces. And the next approach is find the forces. So this q, the forces acting on this q would be, so let's say we have displaced this particular q x distance from the center. Initially the distances between both of these was 2a. That means the midline is at equidistance AA. And what I said, or you can say the question said, that we have slightly displaced it to any side. You displace it to rightwards or leftwards, it will remain the same. So now the new distance comes out to be, new distance after displacement, it becomes a plus x, and the new distance from here becomes a minus x. And at this new position, what shall be the force equivalent? Obviously we have to take new distances now. So the force will be, the net force on this small q will be k capital Q small q by a plus x whole square, that is a repulsive force, plus k capital Q small q divided by a minus x whole square. Now why plus? Rather I would say, in spite of writing plus, it would be better for me to say equal. Okay, why equal? Because as we have said, both the forces are in opposite direction, and I'm not saying that they will be equal. I'm not saying, because if both the forces will be equal, then this small q will stay where it is. Why will it move? So it is very obvious that one force is dominating. Only then this q will oscillate, or will want to oscillate. If both the forces are equal in magnitude, exactly equal in magnitude, this small q will stay where it is. It won't move. So we already know that this leftward force is more than this rightward force. Why? Because this small q is getting a leftward force from this capital Q. And because the distance is less, this force is greater. In this case, the distance is more, so this force is lesser. Henceforth, this force is greater than this force. So we can say, this can be said as, the net force can be said as, net force on Q, small q, can be said as this force minus this force. We cannot say them equal. Why did I showed the sign of equality? So that you can get a clear concept that when to say equal and when not to say equal. Over here, the small q is doing motion, so the net force is not 0. The net force was 0 when it was exactly at the center. We have displaced this small q slightly away from the center. Now the net force is not 0. Now we have a greater force towards the left and a lesser force towards the right. So the first thing that should come into your mind, that the net force acting on q is k capital Q small q by a plus x whole square, that is the greater force, minus k capital Q small q divided by a minus x whole square. Okay, this should be the equation. One more way to attain this equilibrium is by this. You can assume a direction to be positive. If you are getting problems with the sign, what you can do is you can assume the right direction or the positive x-axis as positive direction. So what you will do, you will take this force as positive and this force as negative. Okay, this won't change the answer. Even if I write this reversely, this won't change the answer. The answer will come as expected, so you don't have to worry. The more better approach is to do is you can take a particular axis as positive. So what we have done over here, that we have taken a single direction as positive and we set this force as positive because it was along the direction of positive, and this opposite facing force as negative because we have assumed that the positive x-axis is positive. Now we got an equation. This is very easy. Now listen, we have done only one step. We have done only a single step. We have not done anything extra. The only thing that we did was we found the net force on charge q, that is this much. If you equate this equation, you will get a simpler form. Let's equate it to a simpler form. The simpler form can be written something like this. It will become a lengthy equation, but you have to do it. You have to subtract everything. Let me clear this. Now the thing becomes very clear, very easy. You can do this. Okay, this becomes this and this becomes this. Okay, this denominator can be expressed in a more simpler way, because if you're seeing this, you might assume that this is a very big expression, that this will become very handy. This denominator can be written as a minus a square minus x square whole square. So this is the combined or condensed form of this expression. This expression can be condensed like this. How did this expression come? You might be familiar, a plus b, a minus b equals a square minus b square. So what we did was we have converted a plus b, a minus b as a square minus b square, but because the whole expression was in square, so this also was squared up. So henceforth this condensed form. I hope this is very clear. So we got the denominator condensed as this. Now what we have to do is solve the upper part. So if you solve the upper part, I'm going to slightly peek into the answer and see what the solution of this part is, because it will take time to solve. You can do this at home. So you will get the upper part as, I'm telling you the final extract, that will be k capital Q small q minus will be present 4ax. This shall be the final form. If you equate these two forms, you will get this. Don't worry for that. Okay. And now the final form can be written as, either you can leave k as it is, or you can express k in the terms of 4 pi epsilon naught. This 4 pi epsilon naught comes down, denominator remains as it is. It is only pure maths. We are not doing any physics now. 4 would cut each other and the final expression comes out as k got downwards, capital Q small q ax by pi epsilon naught 4 finish a square minus x square whole square. This is the net force, right? Is this the net force? This was pure maths. We did nothing extra. This was pure maths. Okay, the physics ended over here. F net nikalne mein physics khatam. The only thing that we had was maths. We calculated the F net as this. Now, did I tell you earlier that the equation of SHM is d square x by dt square plus omega square x? What our aim is? Our aim is to find omega. Once you get omega, you will get the time period. So can we express force in this equation? So we have to find a method to express the force that we just got into this expression so that we can find omega. Yes, we can do this. See this. Does the equation has x? Yes. This x is the smaller displacement that we gave to the charged particle. Remember, this x was the small displacement that we gave to the charged particle. If you remember that, I already said while explaining the question that this small q will be displaced slightly with x. So this x is already in the equation and this x is also in the equation of SHM. Now, this makes our question very easy. There are two short methods. Either whatever expression comes with x, this particular value, this particular value can be said as close to omega, but there are some complications that we have to deal over here. Okay, now what are the complications? It would be more correct to equate force with this particular force. What force I'm talking about? Mass into acceleration. Our goal is to relate this net force, electrical force, in the equation of SHM. So what we can do over here, we know that force equals mass into acceleration, and this force can be equal to this, that is minus q small q a x by pi epsilon naught, okay, a square minus x square whole square, right? I'm only doing maths, nothing else. I'm only equating the equations. Can we convert this acceleration as d square x by dt square, right? So now I can say m d square x by dt square equals, I'm only trying to get a format of this equation into the equation of SHM so that we can hold on to omega. Did we say this? M d square x by dt square equals to minus this. When can we place m to the RHS? So when we remove m from here, going to the right hand side, it will come in the denominator. That's it. So we got the value of d square x by dt square. Now what we can do over here, we can shift the RHS to the LHS. So now the equation comes out to be d square x by dt square plus capital Q small q, okay, a x by pi epsilon naught a square minus x square whole square into m. Is this right? No problem with that? Okay. And over here we have to consider this small x as very small. Now we were doing it because this complete equation is an equation of SHM, but the only problem we are getting, that we are getting x at two positions, and we were already told that the x is very small than a, because x is very small, obviously because it is in SHM. So by the method of binomial expression, we can remove this x from this equation. So now the new equation becomes something like this. See to it. Now the new equation becomes, I will copy this downwards and see this what I'm doing, d square x by dt square plus capital Q small q ax by pi epsilon naught. Now what I will be doing is, because this x is very less than a, so we will remove the higher powers of x, because x is very less. In binomial equation we do it this way, and now a becomes a to the power 4 because we have removed x, and the square is now only for a square. So a square ka square becomes a4 times mass. Let me remove this x, or else you will think that this cross is x. Is it the final equation? Can we remove a over here? Okay, we can do this. So now this becomes a cube. From the numerator, a got removed, and now the denominator become a cube. Now we only have x at a single position. Can this equation be related with the general equation of, or standard equation of SHM? If you see clearly, you have these two things as it is, you have x as it is. The only part left is omega square. So we can say it very clearly that this part that we have is omega square, right? So omega square equals capital Q small q by pi epsilon naught a cube m. We are only doing maths, we are doing nothing extra, we are only doing maths. So omega comes out to be under root capital Q small q by pi epsilon naught a cube m. And because omega's expression has been found, time period comes out to be 2 pi by omega. That becomes 2 pi under root pi epsilon naught a cube m by capital Q small q. And hence the time period of the SHM is at your site. And this is the answer. This is the correct answer. Okay. So I hope you found this question interesting. I hope you got a new method of variation. a better way to solve these kind of questions where the SHM can be related with electrostatic force of interaction and how the time period can be deduced from these small oscillations axially or equatorially. The same question can be said if the charge Q is taken to be negative minus Q and now it is displaced equatorially, then again it will start an oscillation path. And now the distance or the time period of oscillation would be. So in that case, what your approach should be, everything will be as it is, only the net force will vary. Only the net force will vary. And the net force will be, because now I said that the intermediate charge is minus Q. So as the intermediate charge is displaced equatorially, as the intermediate charge is displaced on an equatorial axis, it will get a net force along the negative x direction. And this net force can be calculated as minus 2f cos theta. Okay, this angle can be assumed as theta, and the direction towards the positive y-axis can be taken as, the direction towards the plus y-axis can be taken as positive. That is why I have taken minus 2f cos theta, because it's directed towards the lower side, because obviously we are dealing with vectors, so we have to make sure the directions are correct. Even if you don't take the sign, your answer will come with the proper value, so you don't have to worry for that. Okay, the only thing you have to find is net force. Net force expression should be correct. If net force expression is correct, so with this you first have to find this distance. So let's say the displacement was said to be x in the equatorial position and this distance is a. So this distance is under root a square plus x square, right? So whenever you will calculate f net in this situation, you will have to take this particular distance. This distance should be the r of the formula. While calculating force, normally we say F equals K Q1 Q2 by R square. So this shall be the new R now, because this is the direct distance between the charged particles. Okay, so by this you have to calculate the F. From F you will place 2 cos theta, the values of cos theta. So how to take cos theta? Cos theta can be found out by the normal trigonometrical ratio. Cos theta, that can be said as curly base by hypotenuse. So this base, that is x by hypotenuse. So cos theta can be replaced with, in this particular equation, cos theta can be replaced with x by under root a square plus x square. When you solve all of this, you will get a lengthy expression of F net. Again, you have to do the same way that I did. F net has to be equated with MA. MA can be abbreviated as d square x by dt square. So the value of F net and md square x by dt square can be equated. Again, you have to do the same way. Mass would go into the denominator of F net, whatever the expression of F net is, and you shift the complete F net by m to the rightward side along with d square x by dt square to make the expression similar to that of the standard equation of SHM, that is d square x by dt square plus omega square x equals to 0, and along with x, or you can say leaving x, whatever expression comes, that is equal to omega square, and from there again you will get the time period. Okay, so this question is for you. You can try and solve it. And if you see to it, we have solved the first part of the question very correctly. We have solved the first part of the question very correctly with all the things in proper places. The answer comes out to be similar. The second question is almost similar, but this time the charge in the middle is taken as minus q and is slightly displaced not in the axial but in the perpendicular direction to the line joining the charges. And now it is asked to find the time period. So you have to do the same method, but this time only the F net will be different, but all the equation and the standard SHM equation will remain same, and you have to do this in the same way that I did earlier. So you can do this at home. You can pause the video, you can solve for this, and you can find the answer, and you can tell me in my Telegram on my personal DM. Okay, so henceforth this particular part of Coulomb's law is completed. The next lecture we will be focusing on electric field. Okay, and trust me, it is very tough to teach in English, so I would, one lecture is okay for me, but I cannot regularly teach in English. To be very honest, it is a hectic and a kind of slow process for me, because speaking in English takes time to think, and it takes time to बहुत late. It makes things very late, so I cannot do this every day. So just because a student said, so that is why I did this. But it is very tough to teach in English regularly. So the next lecture onwards, it will be a normal lecture. It will be a normal English lecture, English plus Hindi as usual, and that would be better for me, because obviously it takes very time and we don't have much time for the syllabus. We have to speed up things, we have to complete everything in a faster pace, so we don't have much time for this. So I'm really sorry, but I have to do this. I have to be at my comfort to teach. If I'm not comfortable to teach, then it is not possible for me to go up in a faster pace, because speaking in English takes time, needs time to think before saying, and that is a very hectic job. It strains my mind. Rather than teaching, I'm more focusing on my words, so it is tough for me. So from the next lecture onwards, I will be focusing on the lecture and not on my language, and I will give it a sense as I do. Okay, then thank you so much. Thank you for seeing the lecture. The next lecture will be of mole concept, so stay tuned. We are going live again. We will study mole concept, but in my way. Thank you so much. Good night. Revise this once again.